What if the universe is more bizarre than we ever imagined? Beyond our planetary neighbors, strange and unexplained objects whisper the secrets of cosmic mysteries waiting to be unraveled. From exotic planets with impossible weather patterns to galaxies that defy our understanding, each discovery pushes the boundaries of science, opening doors to the unexpected. Unexplainable signals hint at unknown phenomena, while the nature of the unknown invites us to question everything we think we know. As new frontiers in space observation emerge, the potential for alien megastructures and unusual stellar behaviors captivates our imagination and challenges conventional theories. The discoveries of 2024 promise unimaginable insights into these enigmas. Join this exploration of the cosmos, where each answer leads to even greater questions, and prepare to embrace the thrill of the unknown. Space has unveiled some truly strange and intriguing objects that challenge our understanding of the universe. One of the most fascinating is a neutron star, the remnants of a massive star that has collapsed under its own gravity after a supernova explosion. These stars are incredibly dense. Just a spoonful of neutron star material would weigh as much as an entire mountain on Earth. Not only are they fiercely dense, but they also spin rapidly, sometimes sending beams of radiation that sweep through space like lighthouse signals, which we observe as pulsars. Another remarkable object is a rogue planet, a planet that wanders through the galaxy without a star to call home. These solitary worlds float freely in the darkness of space, potentially harboring the conditions for life, even without the warmth of a sun. Their existence raises questions about planetary formation and the dynamics of celestial bodies. Then there's the enigmatic dark matter, which makes up a large portion of the universe's mass, yet eludes direct observation. It doesn't emit light or energy, making it invisible and detectable only through its gravitational effects on galaxies and galaxy clusters. Scientists believe that understanding dark matter could unlock many secrets about the cosmos and the very fabric of reality. Additionally, we cannot forget about the extreme weather observed on some gas giants like Jupiter. Its Great Red Spot is a gigantic storm, larger than Earth itself, that has raged for hundreds of years. This massive cyclone exemplifies the complex atmospheric phenomena that can occur when the conditions are right. Finally, one cannot overlook phenomena like gravitational waves. These ripples in space-time, first predicted by Einstein, were confirmed by direct observation only in recent years. They are produced by some of the most violent and energetic processes in the universe, such as the collision of black holes. Each detection opens a new window into understanding the dynamics of the universe. The cosmos continually surprises us with its mysteries, from solitary rogue planets to colossal storms and the elusive nature of dark matter. Each discovery pushes the boundaries of our knowledge, revealing that space is filled with wonders that are both strange and thought-provoking. Rogue planets, those solitary wanderers that drift through the vastness of space, are fascinating celestial bodies with intriguing origins. Their formation often starts in a similar environment to that of regular planets, typically within a protoplanetary disk surrounding a young star. In these disks, grains of dust and gas clump together over time, creating larger objects that can eventually become planets. However, circumstances can change dramatically. Sometimes, a rogue planet forms when it experiences a violent interaction with other celestial bodies in the same system. This could involve gravitational forces from another planet or a star that are powerful enough to disrupt its orbit. In other cases, a planet might be ejected from its home system due to the gravitational influence of multiple planets vying for stability, forcing one to break free from the gravitational grip of the star. Once ejected, these planets take on a nomadic life, drifting through the cosmos without the warmth or light from a nearby star. Their isolation gives these rogue entities unique characteristics. They might still retain some heat from their formation or have pockets of warmth generated by radioactive decay within their cores. This residual heat allows them to maintain features such as atmospheres or even marginally habitable conditions for extended periods, even if they are cut off from stellar energy. The search for rogue planets not only captivates astronomers, but also helps us understand planetary formation and dynamics in different environments. These lost worlds serve as a reminder of the chaotic nature of the universe, where even a planet can become a wanderer, drifting endlessly through the dark, uncharted realms of space. Ultra-diffuse galaxies are fascinating astronomical objects that challenge our understanding of galaxy formation and structure. These galaxies stand out because they possess an incredibly low density of stars spread over a vast volume. To visualize this, think of a typical galaxy with its bright, tightly packed clusters of stars, often appearing vibrant and colorful. In contrast, an ultra-diffuse galaxy is like a faint fog. There are stars, but they are so sparsely scattered that the galaxy is hardly visible against the backdrop of space. The reason these galaxies have minimal visible matter lies in their composition and formation history. It is theorized that ultra-diffuse galaxies may have formed through processes that either stripped away their gas or stars or prevented them from accumulating the materials necessary to create a denser, more luminous structure. This could occur during interactions or collisions with larger galaxies, which can lead to the removal of their star-forming gas. As these resources diminish, the galaxy's ability to produce new stars declines dramatically, leading to a faint and diffuse appearance. Additionally, it is suggested that many of these galaxies may have an unusually high dark matter content relative to the visible matter they display. Dark matter does not interact with light in the same way that normal matter does, making it invisible to our most powerful telescopes. However, its presence can be inferred from the gravitational influences it has on the motion of stars within these galaxies. Therefore, while ultra-diffuse galaxies may appear insufficiently luminous, they could still harbor vast amounts of invisible dark matter, contributing to their gravitational binding and stability, even as their visible components remain remarkably sparse. This duality of composition raises intriguing questions about the nature and evolution of galaxies in our universe. The idea of stars composed entirely of dark matter presents a fascinating concept, blending current scientific understanding with the mysteries that still envelop dark matter itself. Dark matter, which makes up a significant portion of the universe's total mass, does not interact with light in the way ordinary matter does. Consequently, it cannot be observed directly through telescopes. Instead, it is inferred through gravitational effects on visible matter, such as stars and galaxies. The primary challenge in forming stars made solely of dark matter lies in the nature of this enigmatic substance. Ordinary stars form when gas and dust in space collapse under the influence of their own gravity, igniting nuclear fusion in their cores. Dark matter, however, does not possess the necessary properties to undergo nuclear fusion or collapse into dense objects in the same way. While some theoretical models propose entities known as dark stars, which include both dark matter and normal matter, the concept of a wholly dark matter star is more complicated. In these models, dark matter particles hypothetically interact very weakly, making it difficult for them to clump together tightly enough to form a star-like structure. Without significant interaction, dark matter would spread out rather than coalesce, limiting the possibility of a stable star purely composed of dark matter. Moreover, dark matter's effects on cosmic structures currently point more towards its role as a gravitational framework rather than as a direct source of light and heat typically associated with stars. Therefore, while dark matter may play a critical role in the formation of galaxies and the structure of the cosmos, the existence of stars made entirely of dark matter remains a notion firmly situated in theoretical speculation rather than established reality. Oumuamua is an intriguing cosmic visitor that captured the attention of astronomers around the world when it was first spotted in 2017. Unlike typical asteroids or comets that originate from within our solar system, Oumuamua comes from outside, marking it as the very first interstellar object detected passing through our celestial neighborhood. This elongated and peculiar shape sets Oumuamua apart. Imagine a cigar or a needle dramatically elongated, rotating as it travels through space. This unusual form, combined with its rapid speed, led scientists to theorize about its origin. The object is believed to have traveled from a distant star system, likely eons away, before venturing into our solar system. As it hurtled past the Sun, Oumuamua exhibited mysterious behaviors, such as accelerating in ways that could not be entirely explained by the gravitational pulls of nearby celestial bodies. Some proposed that this might be due to outgassing, the process where gas is expelled from a comet as it warms up near the Sun, but others wondered if it could be a more exotic explanation, perhaps involving unknown spacecraft or unusual materials. The debate over Oumuamua's nature continues, as scientists examine its characteristics to gather insights into the building blocks of the universe and the possible existence of other interstellar objects that might visit us in the future. Oumuamua serves as a reminder of our place in this vast cosmos, where mysteries abound and every discovery could reveal new secrets about our universe. This year has been remarkable for our understanding of the universe, marked by several groundbreaking discoveries that have further illuminated the cosmos. One of the most exciting revelations centers around the detection of gravitational waves, which are ripples in spacetime caused by massive cosmic events like the collision of black holes. Enhanced observatories have allowed scientists to identify these waves with unprecedented clarity, offering insights into the properties of black holes and their formation. Another significant stride involves the exploration of exoplanets, those fascinating worlds beyond our solar system. Researchers have discovered a variety of new exoplanets, some located in their star's habitable zone, where conditions may support liquid water. This discovery fuels the search for potential life beyond Earth, sparking discussions about the kinds of atmospheres these planets might possess and the biological diversity that could be possible. Additionally, advancements in telescopes, notably the James Webb Space Telescope, have provided stunning new images that reveal distant galaxies and the early universe. By peering deeper into space than ever before, scientists can now observe phenomena that occurred billions of years ago, enhancing our understanding of the evolution of galaxies and the overall structure of the universe. Astrophysicists are also revisiting the mysteries of dark matter and dark energy, which together constitute most of the universe's content, yet remain poorly understood. This year has seen pioneering research aimed at better understanding these elusive elements, with experiments designed to detect dark matter interactions or to refine measurements of how dark energy influences the universe's expansion. Together, these discoveries not only enrich our knowledge, but also provoke new questions about the fundamental nature of reality. Each breakthrough contributes to an ever-evolving narrative about our universe, pushing the boundaries of what we thought we knew and inspiring future generations to seek answers to the cosmos's deepest mysteries. In our quest to understand the universe, recent discoveries of new planets have indeed challenged and expanded our understanding of planetary systems. Astronomers have identified a variety of exoplanets, which are planets located outside our solar system that exhibit intriguing characteristics unlike anything we see in our own celestial neighborhood. One particularly fascinating class of exoplanets is known as hot Jupiters. These massive gas giant planets orbit very close to their stars, resulting in incredibly high temperatures. This defies our initial expectations because in our solar system, gas giants are found much farther from the Sun. The existence of hot Jupiters suggests that planetary formation and migration processes can be much more dynamic than previously thought. It raises questions about how these large bodies can form far from their suns and then move into such tight orbits. Another surprising discovery involves planets that challenge the concept of planetary diversity. Some of these newly found worlds are classified as super-Earths, which are rocky planets with masses greater than Earth's but significantly less than that of Neptune. Their variations in composition, atmosphere, and interaction with their host stars show that there is a much wider range of potential climates and conditions for habitability than we once considered. Moreover, the detection of planets with unusual orbital arrangements has illuminated the complexity of planetary systems. For example, some planets orbit in highly eccentric paths, unlike the nearly circular orbits we see in our solar system. These peculiar orbits suggest that gravitational interactions with other bodies, possibly including the influence of multiple stars, play a crucial role in shaping planetary relationships. These discoveries not only challenge our existing models, but also invite us to rethink the very processes involved in planet formation and evolution. As we refine our methods for observing distant worlds, we continue to encounter new surprises that broaden our understanding of the cosmos and the diversity of planetary systems existing throughout the universe. Each new planet found is a piece of a larger puzzle, revealing the intricate and varied nature of the galaxies beyond our own. In 2024, scientists made fascinating observations regarding the cosmic microwave background, which is the faint afterglow of the Big Bang. This background radiation offers a glimpse into the infant universe, acting as a cosmic snapshot of a time when the universe was just a fraction of a second old. Unexpectedly, researchers noted anomalies in the temperature fluctuations across the background. These fluctuations are essentially tiny variations in the radiation's intensity, which indicate how matter was distributed in the early universe. The new data revealed areas with unexpected patterns, suggesting structures that should not have emerged so early in cosmic history. Linking this to dark matter, the observations hinted at a potential correlation between the density of this elusive material and the anomalies. As dark matter constitutes a significant part of the universe, understanding its influence could explain the unusual patterns seen in the cosmic microwave background. Furthermore, some researchers proposed that these anomalies might offer insights into potential new physics, possibly hinting at interactions or elements previously unaccounted for in established models of cosmology. These findings encourage scientists to rethink aspects of the universe's early moments, opening avenues for further investigation. Such revelations not only advance our understanding of cosmic history, but also pose intriguing questions about the fundamental nature of the universe itself. As more analyses are conducted, this fresh perspective could reshape our comprehension of the cosmos and its intricate workings. Throughout our exploration of the cosmos, we have detected several signals that have sparked excitement and speculation about the possibility of extraterrestrial life. One of the most notable examples occurred in 1977 when astronomer Jerry R. Ehman recorded a strong, narrow-band radio signal while working on a SETI project, the search for extraterrestrial intelligence. This signal, which lasted for 72 seconds, was so striking that Ehman scrawled "Wow" in the margin of the printout, giving it its lasting name. While numerous efforts have been made to determine the origin of that signal, scientists have yet to find conclusive evidence linking it to alien civilizations. More recently, astronomers have identified other peculiar radio signals that exhibit unusual characteristics or originate from distant galaxies. These signals often vary in frequency or pattern, which raises questions about their nature. Some of these discoveries might have natural explanations, such as pulsars, rapidly spinning neutron stars that emit beams of radiation, or other astrophysical phenomena. It is also important to understand the vast distances involved in our universe. Even if we detect intriguing signals, they may not necessarily imply intelligent life. The universe is rich with the potential for natural events that can generate complex signals, making the search for signs of life a challenging endeavor that requires careful analysis and confirmation. While we have found mysterious signals that could potentially hint at alien life, there remains no definitive evidence. Yet, the search continues to inspire curiosity and drive exploration, reminding us of how much we have yet to learn about the cosmos and our place within it. In the vast stretches of the universe, astronomers continue to uncover galaxies that challenge our existing models and refresh our understanding of cosmos. One notable discovery is the population of ultra-faint dwarf galaxies. These extremely small galaxies are teeming with dark matter, yet hold very few stars. Their existence questions the traditional ideas of galaxy formation, suggesting that many more of these faint structures could exist, hiding in the shadows of brighter galaxies. Another astonishing find is galaxies that are forming stars at astonishing rates, particularly notable in the early universe. Known as starburst galaxies, these celestial objects create new stars at a pace that contradicts previous theories about how quickly galaxies can evolve. They push the boundaries of our models and suggest that the conditions in the early universe allowed for dramatic bursts of star formation, an activity that could reshape our ideas about galaxy evolution. Additionally, researchers have identified galaxies displaying an unusual amount of metallicity, elements heavier than hydrogen and helium. Some of these galaxies contain a surprisingly high concentration of these elements despite being very old and thought to have formed earlier in the universe's history. Their composition raises questions about the processes of star formation and metal enrichment and challenges the models predicting how materials are recycled in the cosmic cycle. Furthermore, the discovery of massive galaxies that existed much sooner after the Big Bang than expected poses a significant dilemma. These colossal entities, with their abundance of stars and structures ready to host life, suggest that our timelines for galaxy formation are misleading. They hint at the possibility that the universe may have evolved far more quickly than our current models can account for. These discoveries not only excite researchers, but also underline the universe's complexity, revealing just how much we have yet to learn about cosmic evolution. Each finding serves as a reminder that our cosmic models are continuously in flux, adapting as we peer deeper into the fabric of space and time. Hot Jupiters are a fascinating category of exoplanets that are similar in size and composition to Jupiter, but orbit extremely close to their host stars. Imagine a giant gas planet, often several times the mass of Earth, positioned so near to its sun that its surface temperature skyrockets, making it vastly hotter than its distant cousin, the cold gas giants of our solar system. The reason these planets orbit so closely is largely tied to the forces at play during their formation and evolution. Originally, when a planetary system forms, these giant planets might start far from their stars, in cooler areas where gases can condense. However, through complex gravitational interactions and migrations within the young planetary system, these planets can be nudged from their distant orbits into much tighter ones. This migration could involve interactions with other planets or the protoplanetary disk, the cloud of gas and dust that surrounds a young star. Once a hot Jupiter settles into its close orbit, the intense heat from its star influences its atmosphere significantly. The energy is so great that it creates a thick, swirling atmosphere that can be radically different from what we see on Jupiter. As a result, hot Jupiters can reveal insights into planetary formation, climate, and the dynamics of solar systems far beyond our own. These impressive worlds challenge our traditional understanding of planetary formation and demonstrate the diverse array of conditions in the universe. The concept of planets composed entirely of diamond or other rare materials captivates our imagination. While it might sound like science fiction, there is indeed scientific basis for the existence of such celestial bodies. Diamonds form under extreme conditions of heat and pressure, typically found deep within the Earth. However, rough estimates suggest that giant planets made predominantly of carbon, which could crystallize into diamond under appropriate conditions, may exist in our universe. For instance, researchers believe that the interiors of some gas giants could contain vast amounts of carbon, potentially leading to diamond formation deep within their cores. One noteworthy candidate for this intriguing idea is a planet named 50 Cancri e, located about 40 light-years from Earth. This planet is classified as a super-Earth, a type of planet larger than our own but significantly smaller than those gas giants. Scientists speculate that its high carbon content and extreme pressure might mean that a portion of its surface is composed of diamond. Beyond diamonds, the cosmos could harbor planets home to other rare materials. For example, certain exoplanets may have conditions that allow the formation of metals or complex minerals in ways we have yet to fully understand. The diversity of materials could arise from the unique histories of these planets, including their formation processes and the elements available in their star systems. While finding a planet made entirely of diamond remains an unlikely scenario, the universe holds a multitude of secrets. Ongoing advancements in technology and astronomical observation may one day allow us to confirm or disprove these hypotheses, bringing us one step closer to understanding the incredible variety of planetary compositions that exist beyond our solar system. Super-Earths are fascinating exoplanets that exceed the size of Earth, but are still smaller than the gas giants like Neptune or Uranus. These planets typically consist of solid surfaces and can exhibit a variety of characteristics, ranging from rocky landscapes similar to our own planet to thicker atmospheres that might harbor various gases. The intriguing feature of super-Earths is their potential to maintain conditions suitable for liquid water, which is essential for life as we understand it. The reason super-Earths appear to be prevalent in our galaxy can be linked to the mechanisms of planetary formation. When a star forms, it gathers material from a surrounding disk of gas and dust. Many small building blocks, or planetesimals, clump together due to gravitational attraction. As these planetesimals accumulate, they can create these super-Earths more easily than larger gas giants. Specifically, the combination of abundant rocky material and favorable conditions allows for the development of these intermediate-sized planets. Additionally, the detection methods we use today, notably transit and radial velocity techniques, are particularly adept at identifying larger, closer planets. Since many super-Earths occupy orbits near their stars, we can observe these transits more frequently, allowing researchers to spot them more readily compared to distant, smaller, or more massive planets. The sheer variety of environments within these super-Earth classifications raises questions about their atmospheres, potential geological activity, and the possibility of harboring life. Each discovery informs us about the diverse conditions that can exist beyond our solar system, marking super-Earths as key players in our understanding of planetary systems in the universe. When we think of rings in our solar system, Saturn's magnificent rings often come to mind, shimmering with stunning beauty and enormous scale. However, while Saturn's rings are the most iconic and substantial we know of, they are not the only rings present in our solar system, and they may not even hold the crown for size or mass in the grander cosmic scene. In fact, several other gas giants also possess ring systems, including Jupiter, Uranus, and Neptune. But their rings are generally smaller, fainter, and less massive compared to Saturn's. Jupiter's rings, for instance, are thin and made up of tiny particles, primarily dust, moving at incredibly high speeds. Uranus and Neptune also have rings that are quite faint and not as visually striking as those of Saturn. Yet, when we step beyond our solar system, the hunt for massive ring systems takes an intriguing turn. Astronomers have discovered exoplanets, or planets outside our solar system, that may have expansive and dense ring systems. Some of these rings could potentially rival or even surpass the rings of Saturn in terms of mass due to the sheer amount of material orbiting these planets, though hard evidence and direct observation of such systems remain a challenge. As our technology advances and we explore further with telescopes and missions designed to peer into the distant universe, we may uncover new worlds with incredible rings, prompting us to rethink what we know about planetary ring systems and their characteristics. So, while Saturn's rings currently reign supreme in our understanding, the universe holds many mysteries, and there are likely planets out there that defy our expectations. The idea of planets with oceans of molten metal or liquid glass challenges our conventional understanding of planetary environments. In the realm of possibility, such planets could indeed exist under specific circumstances. Consider a planet orbiting a star at an incredibly close distance, where temperatures soar high enough to melt metals like iron or nickel. The extreme heat would create vast pools of molten metal resembling oceans, but with a surface much different from what we see on Earth. Instead of being fluid and reflective like water, these metal oceans would exhibit unwanted viscosity and a shimmer that betrays their composition. This kind of environment would be inhospitable to life as we know it, existing in conditions of intense heat and pressure. The discovery of extraordinarily large black holes at the centers of certain galaxies raises intriguing questions about their origins and development. These supermassive black holes, often millions or even billions of times the mass of our Sun, sit at the heart of galaxies like the Milky Way. Their presence can be attributed to several fascinating processes. Initially, black holes can form from the remnants of massive stars that have exploded in supernovae. However, in the case of supermassive black holes, we must consider the environment of a galaxy as a key factor. During the early stages of the universe, dense clouds of gas and dust collapsed under their own weight, leading to the rapid formation of stars. As these stars formed and evolved, they generated enormous amounts of energy, further fueling the surrounding gas. This chaotic environment enabled some black holes to grow rapidly by consuming gas and merging with other black holes. Additionally, gravitational interactions within the dense centers of early galaxies could have played a significant role. When galaxies collide or merge, their central black holes can spiral toward each other due to gravitational attraction. When two black holes merge, they can create an even larger one, leveraging the energy released in the process. Through repeated cycles of merging and accretion, the process of gathering mass by attracting surrounding material, black holes can achieve immense sizes. Moreover, the intricate balance between star formation and black hole growth highlights a profound relationship within galaxies. As supermassive black holes grow, they can influence their surroundings, regulating star formation through mechanisms like stellar winds and energetic jets. This interplay shapes the galaxy itself, creating a complex, evolving system where the central black hole and its host galaxy grow and change together. The presence of unusually large black holes at the centers of galaxies is a result of their dynamic formation history. Factors such as rapid gas accretion, mergers with other black holes, and interactions within galactic environments contribute to the remarkable sizes we observe today. Understanding these cosmic giants offers insight into the evolution of galaxies and the universe itself. Zombie galaxies are fascinating cosmic entities that have reached a point in their evolution where they have ceased the incredible process of star formation. Imagine a vibrant and bustling city that suddenly goes silent, where no new buildings are constructed and the liveliness fades into an eerie stillness. This is similar to what happens in a zombie galaxy. It appears to be intact and functional, but is actually dormant, with little to no new stars being birthed. The key factor behind this phenomenon lies in the depletion of the galaxy's gas reserves. Initially, galaxies are like factories, filled with raw materials needed to create new stars. Over time, as these stars are born, they consume the gas available to them for fusion. When a galaxy runs low on this essential gas, it becomes unable to form new stars effectively. Additionally, external influences can play a significant role. For instance, interactions with other galaxies, such as mergers or gravitational pulls, can disrupt the gas supply or expel it into space. Environmental factors can also contribute. A galaxy situated in a dense cluster may lose gas due to the forceful winds generated by the cluster's many stars. The result is a zombie galaxy. It may still exist, housing older stars that continue to shine, yet it is essentially lifeless in terms of star formation. Understanding these celestial remnants contributes to our broader comprehension of the life cycles of galaxies and the universe's evolving fabric over immense timescales. The existence of galaxies as we know them hinges significantly on dark matter. To understand this relationship, imagine building a large structure. If the foundation is weak or missing, the entire structure may lack stability. Dark matter acts as the unseen scaffolding of galaxies, providing the crucial gravitational forces necessary for their formation and cohesion. When a galaxy forms, vast clouds of gas and dust collapse under gravity, eventually igniting the processes that lead to stars and planets. However, observations show that visible matter, the stars, planets, and gas, makes up only a small fraction of what contributes to a galaxy's total mass. The remainder, thought to be dark matter, fills in the gaps, exerting gravitational influence and holding everything together. Without dark matter, the rotation speeds of stars within galaxies would not match the distribution of visible matter. Stars orbiting at the edges of a galaxy would move much slower than we observe if only the visible matter was present. This discrepancy suggests that there's significantly more mass at play, which we cannot see directly. Thus, dark matter's presence ensures that galaxies can maintain their structure and stability over billions of years. In a universe devoid of dark matter, the gravitational pull necessary for galaxies to form, hold together, and evolve would be insufficient. They might still form under different conditions, but would be drastically different in size, shape, and behavior, likely lacking the rich complexity we observe today. While one can speculate about alternate forms of matter or different cosmic conditions, the specific combination of visible and dark matter we see is foundational for the universe we inhabit. Starburst galaxies are fascinating celestial phenomena characterized by an exceptionally high rate of star formation, often many times greater than that of a typical galaxy. Imagine a vibrant garden bursting with blooming flowers, each representing new stars emerging from clouds of gas and dust. In starburst galaxies, this process is so intense that massive stars ignite in rapid succession, filling the cosmos with brilliant light. The driving force behind this frenetic activity often stems from galactic interactions, such as mergers or close encounters with other galaxies. When galaxies collide or draw near to one another, their gravitational forces can trigger a gravitational dance. This interaction compresses the gas within the galaxies, creating conditions ripe for star formation. Under these circumstances, large amounts of gas and dust are funneled into dense regions where gravity takes over, leading to the birth of new stars at a remarkable pace. Additionally, starburst galaxies are sometimes fueled by the infall of gas from their surroundings, known as primordial gas. This process can replenish their star-forming fuel, allowing the creation of stars to continue at a vigorous rate. As these newly formed stars evolve, they can also influence their environment through intense radiation and stellar winds. This feedback can either trigger further star formation or disrupt existing gas clouds, leading to a dynamically evolving life cycle in these vibrant galaxies. Starburst galaxies showcase the explosive and beautiful moments of star creation, illustrating the dynamic processes that govern the life cycle of the universe. They remind us how the interplay of gravity, gas, and galactic evolution can spark extraordinary bursts of activity in the cosmos. Giant elliptical galaxies are remarkable structures, and their ability to maintain such immense forms is due to several interrelated processes. Firstly, their size and mass come from the accumulation of stars, gas, and dark matter over billions of years. Unlike spiral galaxies, which are characterized by rotating disks of stars and gas, elliptical galaxies are more three-dimensional and typically lack a significant amount of dust and gas. The key to their stability lies in the gravitational forces at play. The sheer mass of a giant elliptical galaxy creates a powerful gravitational pull that holds its stars and other materials together. This gravity prevents the galaxy from dispersing and helps maintain its structure. As stars and matter are drawn in, they often merge with other stars or groups of stars, leading to the formation of a dense stellar core. In addition to gravity, the dynamical processes within the galaxy help sustain its structure. During the lifetime of a giant elliptical galaxy, interactions and mergers with smaller galaxies contribute to its growth. These mergers often result in the redistribution of mass and energy throughout the galaxy, helping to avoid any potential instabilities. The result is a smooth distribution of stars and stellar remnants, which further bolsters the galaxy's gravitational grip. Moreover, the stars in elliptical galaxies tend to have random orbits rather than the organized spiral patterns seen in their spiral counterparts. This random distribution of stellar motions spreads out the gravitational forces more evenly, providing a stabilizing effect. With less angular momentum involved, the stars in elliptical galaxies simply drift through space rather than being corralled into a rotating disk. Ultimately, the combination of mass accumulation, gravitational binding, dynamical stability, and the characteristics of stellar motion all play critical roles in preserving the massive structures of giant elliptical galaxies, allowing them to endure through cosmic time. Fast radio bursts, often referred to as FRBs, are brief but immensely powerful flashes of radio waves originating from distant galaxies. Imagine these bursts as cosmic signals that last mere milliseconds, yet they unleash energy equivalent to what the Sun emits over several days. Discovered in 2007, these enigmatic bursts have taken the astronomical community by storm, sparking intense curiosity and investigation. Currently, scientists have identified several dozen of these events, but their origins remain mostly shrouded in mystery. Some hypotheses suggest that they could result from astronomical phenomena like collapsing neutron stars or the merging of black holes. However, none of these theories has been definitively proven. The difficulty in pinpointing their sources lies in their fleeting nature and the vast distances they travel across space, which can distort and scatter their signals. Furthermore, FRBs present a significant challenge due to their appearance in unpredictable patterns and locations, making it hard to gather extensive observational data. Researchers must rely on advanced telescopes that can capture these transient events. Despite months or even years of scrutiny, the exact mechanisms behind FRBs remain elusive, leading to various speculative theories. Each discovery brings new questions, fueling an ongoing quest to understand these cosmic enigmas and their implications for our understanding of the universe. Supernovae are among the most powerful and energetic events in the universe, marking the explosive death of a star. While scientists have classified several types of supernovae, the possibility of unknown types is very much on the table. The classification we currently use stems from our observations, but the universe is vast and complex, often revealing surprises that challenge our existing frameworks. One key factor is the plethora of stellar masses and compositions. Stars exist in a multitude of forms, with various materials and fusion processes at play. Some stars might end their lives in ways that do not fit neatly into our established categories, leading to potential new supernova types. Additionally, the environments in which stars evolve can be vastly different, influencing their death throes in unexpected ways. Moreover, observational technology continues to advance. As telescopes improve and new methods of detection are developed, we are more likely to uncover events that we currently miss or cannot adequately classify. For instance, a newly detected explosion could reveal characteristics that don't correspond with the known types, suggesting a new class entirely. Furthermore, theoretical work in astrophysics continues to propose mechanisms for supernovae that are not yet observed. Ideas such as supernovae driven by unusual stellar interactions or unique types of core collapses could point to phenomena distinctly different from the known supernova, hinting at exciting discoveries yet to come. The universe is a continually unfolding mystery, and while we have made great strides in understanding supernovae, the exploration of their types is far from complete. As we push the boundaries of our knowledge, the potential for unknown supernova types remains an intriguing possibility that could reshape our understanding of stellar evolution and the cosmos itself. The Great Attractor is a massive gravitational anomaly located in the direction of the Centaurus constellation. Its influence is so strong that it appears to be drawing galaxies, including our own Milky Way, towards it. To understand why this is happening, we need to consider the immense amount of mass the Great Attractor contains. Scientists believe that the Great Attractor is not just one single object, but a cluster of galaxies and dark matter, an unseen substance that makes up a significant portion of the universe's total mass. Just as a magnet pulls metal objects towards itself, the gravitational force stemming from this colossal concentration of mass attracts nearby galaxies, pulling them closer in a journey through space. This phenomenon can be visualized as a ripple effect in a fabric. When you place a heavy object in the center, it creates a dip, causing smaller objects around it to roll inward. Similarly, the Great Attractor creates a distortion in the fabric of spacetime, influencing the motion of galaxies across vast distances. As these galaxies move, they are not just traveling through empty space. Instead, they are following the contours created by the gravitational pull of this immense attractor. Moreover, our position in the Milky Way complicates our view. We are embedded in a swirl of cosmic structures obscured by dust and gas, making direct observation challenging. Yet, through indirect methods, astronomers can infer the gravitational effects that suggest the presence of this powerful region. The Great Attractor is a fascinating reminder of how interconnected galaxies are, driven by forces that shape the cosmic landscape over billions of years. Pulsars are fascinating celestial objects, often described as highly magnetized, rotating neutron stars. These remnants form when a massive star runs out of fuel and undergoes a supernova explosion. The extraordinary conditions generated by this event lead to a dense core that compresses mass into an astonishingly small volume, creating a neutron star. As the neutron star spins, which can happen incredibly fast, sometimes hundreds of times per second, it generates a powerful magnetic field. This magnetic field is not aligned with the spin axis, causing the radiation emitted from the star's magnetic poles to be concentrated into beams, similar to how a lighthouse emits light. As these beams rotate, they sweep across space. What makes pulsars particularly captivating is their precision. The rotation of the neutron star is remarkably stable, akin to the ticking of a highly accurate clock. This stability arises from the star's enormous density and rapid rotation, which keep its rotation constant over long periods. When the beam of radiation crosses the Earth's line of sight, we detect it as a pulse. The intervals between these pulses are incredibly regular, allowing astronomers to measure time with great accuracy. The intense beams of radiation are produced by the acceleration of charged particles along the pulsar's magnetic field lines. These particles gain high energy and radiate as they spiral along the magnetic field, emitting electromagnetic radiation that can range across various wavelengths, including radio waves and even X-rays. The combined effects of a strong magnetic field, rapid rotation, and the dynamics of charged particles result in the precise and intense beams for which pulsars are famous. Cosmic rays are energetic particles from space that continually bombard our planet. They primarily consist of protons, but they can also be made up of heavier nuclei, electrons, and even photons. These high-energy particles originate from various astronomical sources, such as the Sun, supernova explosions, and active galactic nuclei. The detection methods we currently employ have given us a solid understanding of known cosmic rays, primarily focusing on the more common particles. However, the universe is vast and complex, and it is certainly possible that other types of cosmic rays exist, ones that remain elusive to our current detection capabilities. For instance, hypothetical particles from outside the standard models of physics could exhibit unique properties. Some scientists propose the existence of dark matter particles, and if they do interact with normal matter, they may form a form of cosmic radiation that we have yet to confirm. Additionally, beyond the common heavy ions, there could be exotic particles such as primordial black hole remnants or even miniature black holes that could emit different forms of radiation. Furthermore, the energy spectrum of cosmic rays shows a mysterious prevalence of ultra-high energy particles that exceed the energies we can currently produce on Earth. These may arise from interactions and events in extreme astrophysical environments that we have yet to fully explore or understand. As our detection techniques and technology improve, especially with the advent of more advanced telescopes and particle detectors, we will have new opportunities to discover and study these potential cosmic rays. Each new finding could rewrite our understanding of the universe, opening doors to deeper mysteries and greater insights into the fabric of space and time. The quest for these invisible particles could reveal phenomena that challenge everything we think we know about cosmic physics. The concept of time flowing backward ignites curiosity and sparks the imagination about the nature of our universe. In theoretical physics, time is often viewed as a dimension similar to space, progressing in a particular direction, which we experience as moving from the past to the future. However, some cosmological theories suggest that alternate universes could indeed allow for different flows of time. Imagine a universe where the laws of physics are altered in such a way that time flows in reverse. In that scenario, cause and effect would operate in a reversed order. Rather than causing events to unfold, actions would become a consequence of future occurrences. For instance, you might see a glass shatter and then reassemble itself, returning to its original state. The idea often relies on understanding entropy, which is a measure of disorder within a system. According to the second law of thermodynamics, entropy tends to increase over time in our universe, leading to a direction we call the arrow of time. In a universe where entropy were to decrease, this might suggest a reverse flow, creating conditions for time to run backwards. While fascinating in theory, this concept raises significant paradoxes and questions. Would memories be preserved in reverse, or would one experience the world in a fundamentally different manner? Would living beings aging backward create communities that exist uniquely? Such reflections lead us into philosophical territory about the nature of existence itself. Ultimately, the existence of a universe where time flows backward remains speculative. However, exploring these ideas sheds light on the fascinating nature of time and reality, pushing the boundaries of our understanding and encouraging us to think beyond the limits of our own experience. The theory of mirror matter presents a fascinating concept that suggests the existence of a parallel type of matter, fundamentally similar to the ordinary matter that makes up everything we see around us. Imagine our universe as a large tapestry, where conventional matter is represented by one side of the fabric, and mirror matter exists as a mirror image on the other side. While ordinary matter consists of protons, neutrons, and electrons, mirror matter would be composed of counterparts like mirror protons and mirror electrons that interact only through gravity and possibly very weak forces. This theory could provide explanations for various unexplained phenomena. For instance, the enigma of dark matter, an invisible substance making up a significant part of the universe's mass yet not interacting with light, could potentially be addressed by mirror matter. If mirror matter exists, it might account for the gravitational effects observed in galaxies and galaxy clusters that cannot be explained by the visible matter alone. Additionally, consider the issue of missing energy in certain particle physics experiments. If particles occasionally transform into their mirror counterparts, they could escape detection, creating a sort of energy deficit. This transformation might explain why some experiments yield results that do not align with our current understanding of physics. Furthermore, mirror matter poses intriguing ideas about cosmic events. If it interacts with regular matter during collisions or cosmic events, it might lead to unusual energy distributions that challenge our existing theories about particle interactions. The possibility of interactions between these two forms of matter could unlock new avenues of research and offer deeper insights into the fundamental workings of the universe. Mirror matter invites us to contemplate a universe that is richer and more complex than we perceive. By exploring this theory, scientists hope to shed light on some of the darkest mysteries lurking in the cosmos, potentially revolutionizing our understanding of fundamental physics. The mysteries of dark matter and dark energy have puzzled scientists for decades, leading to intriguing questions about their nature and relationship. Dark matter is thought to be a substance that does not emit or absorb light, making it invisible to conventional observations. Its presence is inferred from the gravitational effects it has on visible matter, such as stars and galaxies, which behave as if there is much more mass present than what we can see. This unseen mass is critical in holding galaxies together and shaping the structure of the universe. On the other hand, dark energy is an enigmatic force believed to drive the accelerated expansion of the universe. While dark matter pulls things together through its gravitational influence, dark energy appears to push galaxies apart, counteracting gravity on a cosmic scale. It constitutes a significant portion of the universe, suggesting that its effects dominate the wider cosmic landscape. The idea that these two phenomena could be manifestations of a single unified entity is indeed a compelling hypothesis. Some theorists propose that both dark matter and dark energy may arise from a common source, possibly linked through intricate quantum processes or as part of a more extensive framework that governs fundamental forces. This unified approach could reshape our understanding of gravity and the structure of space-time. However, as appealing as this idea is, we currently lack direct evidence to confirm this connection. Distinguishing between the two remains a challenge, and ongoing astrophysical observations and experiments are aimed at uncovering the underlying truths. For now, dark matter and dark energy remain distinct enigmas, each playing a crucial role in the cosmos, yet their potential relationship continues to inspire research and exploration into the unknown frontiers of modern physics. The idea that space could be filled with unseen structures influencing its shape is a fascinating concept rooted in both theoretical physics and cosmology. To understand this notion, we can think about how the universe behaves on a grand scale. Space is not merely an empty void. It contains various forms of matter and energy that shape its characteristics. Consider how gravity works. Massive objects, like stars and galaxies, create a gravitational field that causes the space around them to curve. This curvature dramatically influences the paths of celestial bodies moving within that space. If we expand this idea, we realize that the universe could also harbor more mysterious structures such as dark matter and dark energy, which are not directly visible but have a profound impact on the cosmos. Dark matter, for instance, makes up a significant portion of the universe's total mass, yet it does not emit light or energy that we can detect. Its presence is revealed through its gravitational effects on visible matter. Similarly, dark energy is a force that seems to be driving the accelerated expansion of the universe. Its nature is largely unknown, yet it plays a critical role in shaping the future of cosmic evolution. Additionally, some scientists theorize about the existence of cosmic strings, hypothetical one-dimensional defects in the fabric of space-time that could stretch across vast distances. These structures, if they exist, could influence the motion of galaxies and the overall curvature of space. While we may not be able to see these potential structures, they could be woven into the very fabric of our universe, guiding its expansion and formation in profound yet subtle ways. As our observational capabilities advance, we might one day uncover the intricacies of these hidden influences, offering deeper insights into the nature of space itself. The idea of black holes serving as wormholes is indeed a tantalizing concept, steeped in the imagination of scientists and science fiction enthusiasts alike. To understand this, we need to look at what both phenomena are. A black hole is formed when a massive star collapses under its own gravity, creating a point of infinite density known as a singularity, surrounded by an event horizon. This horizon marks the point beyond which nothing, not even light, can escape the black hole's pull. Wormholes, on the other hand, are theoretical passages that could connect two separate points in spacetime. You can visualize it like a tunnel through a mountain. Instead of taking a long path around, a wormhole could shorten the journey by directly linking two distant locations. The intriguing thought is that black holes could potentially act as one end of a wormhole, with a matching exit elsewhere in the universe. However, this theory presents several challenges. For one, the immense gravitational forces near a black hole would likely destroy anything attempting to traverse it. Furthermore, even if a stable wormhole were to exist, it would require exotic matter to keep it open, a substance that we have yet to discover. Thus, while the notions of black holes as wormholes opens a fascinating door to possibilities in astrophysics, we remain in the realm of speculation. The realities of physics as we understand it today present significant barriers to confirming this idea. For now, black holes are known for their mysterious nature and powerful gravitational pull, leaving the question of their wormhole potential suspended in scientific curiosity. The year 2024 brought remarkable discoveries in the realm of radio astronomy, revealing mysterious signals that captivated scientists and enthusiasts alike. One of the most intriguing was a series of fast radio bursts, short yet powerful flashes of radio emission from distant galaxies. They appeared sporadically, exhibiting patterns that hinted at their origins. This time, however, the signals were notably more complex, involving consistent repetition that suggested a possible artificial source or as yet unknown cosmic phenomena. Another fascinating anomaly was a signal that emanated from a nearby star system, intriguing researchers due to its unusual modulation and frequency. Unlike past emissions associated with celestial bodies, this signal displayed characteristics reminiscent of engineered waves, leading to speculation about potential extraterrestrial technology. While these claims prompted cautious enthusiasm, scientists emphasized that more data is required to confirm their origins and meanings. Additionally, some radio telescopes detected bursts with unusual polarization patterns that did not align with known astrophysical sources. This raised questions about their physical mechanisms, pushing scientists to rethink their understanding of magnetic fields and radiation processes in space. Each detection sparked debates and fueled imaginations as researchers worked rigorously to unearth the truths hidden within these radio waves. The fascination these signals brought lies not only in their scientific significance, but also in the profound implications they carry about our place in the universe. With each new discovery, humanity edges closer to unraveling the mysteries that lie beyond our planet, igniting curiosity about what other cosmic messages might be waiting to be uncovered. Pulsars are fascinating celestial objects that serve as cosmic lighthouses. These highly magnetized, rotating neutron stars emit beams of radiation out of their magnetic poles. As the star spins, these beams sweep across space, creating a pulsing effect, much like a lighthouse beam illuminating the surrounding area. The regularity of these pulses, often occurring at intervals of mere seconds or even milliseconds, leads many to wonder about their potential to convey messages. The idea of pulsars sending messages, however, requires a more nuanced understanding. Current scientific consensus suggests that the signals received from pulsars are natural phenomena, produced by the laws of physics and not intentionally designed communications. The patterns of these pulses can be profoundly regular, demonstrating extraordinary stability over cosmic timescales, which is a hallmark of their nature. However, interpreting these signals as a form of messaging implies a purposeful design, which we have yet to find evidence for. That said, some researchers do entertain the possibility of uncovering unknown patterns. In an age where data processing and analytical tools are ever evolving, the vast amount of information pulsed out by these stars might harbor subtle complexities or anomalies that we have not yet grasped. While scientists continuously analyze pulsar data for irregularities, presumed communication efforts from extraterrestrial sources remain speculative. If we were to identify patterns that do not conform to the expected behavior of pulsars, it could provoke intriguing questions about their nature. Such discoveries would prompt further investigation and potentially open new avenues in astrophysics and our understanding of the universe. However, as of now, pulsars are best understood as intriguing astronomical phenomena rather than intentional messengers. The quest continues, as every new finding brings us closer to understanding not only pulsars, but the vast, mysterious cosmos around us. The WOW signal is a mysterious burst of radio waves detected in the 1977 by astronomer Jerry R. Ayman. For a full 72 seconds, this signal stood out against the cosmic background noise, suggesting it might be extraterrestrial in origin. If such a signal could be explained and verified as a transmission from an intelligent civilization, it would be revolutionary. First, it would provide compelling evidence that we are not alone in the universe. This realization could shift the focus of scientific inquiry, motivating more rigorous searches for extraterrestrial intelligence. If we confirm that this signal originates from a distant source and is a deliberate transmission, it would open a floodgate of questions about the nature of that civilization, its technology, culture, and potential motives for reaching out. Furthermore, the study of the WOW signal could lead to a new understanding of communication technologies used by advanced civilizations. Learning how they generate such signals might inspire breakthroughs in our own technology, offering unprecedented advancements in long-distance communication. The implications stretch beyond science into philosophy, impacting our views on humanity's place in the universe. The possibility of deciphering the signal itself could unlock insights into the fundamental nature of life beyond Earth. What kind of message might it convey? Could it contain information about their world, knowledge, or even warnings based on their experiences? The excited pursuit of answers could unify people in a shared quest for knowledge. The significance of the WOW signal lies not just in the potential discovery of extraterrestrial life, but in how it could transform our scientific, technological, and philosophical landscapes. It urges us to reconsider our understanding of life, intelligence, and the vast cosmos in which we exist. In the vastness of space, where silence reigns and distances are unfathomable, the quest to decode signals becomes an intriguing venture. Scientists constantly monitor the cosmos for signals that could indicate the presence of extraterrestrial intelligence. However, amidst the cosmic chatter, some signals can easily be misinterpreted as natural phenomena when they might actually originate from artificial sources. Consider the natural sources of radio waves, such as pulsars, highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. Their signals can repeat with such precision that they may resemble a deliberate communication pattern. Similarly, certain types of solar activity or interactions between cosmic rays and matter in space can generate bursts of radiation that might mimic structured signals. The challenge lies in distinguishing these naturally occurring signals from those that could be engineered by intelligent beings. A signal's frequency, pattern, and modulation can sometimes suggest intelligence, yet without a comprehensive understanding of its origin or context, definitive conclusions remain elusive. Detection techniques often involve comparing unusual signals against a backdrop of known cosmic phenomena, and what initially seems like artificial communication may turn out to be a cosmic illusion. Additionally, the vast range of conditions in space creates a complex environment where natural processes can produce unexpected and intricate patterns that could mislead observers. As humans continue to refine their listening efforts, they must remain vigilant and open to the possibility that what we perceive could misrepresent the true nature of the universe's signals, blurring the lines between the natural and the artificially constructed. This exploration beckons a deeper understanding of our cosmic surroundings and raises profound questions about our place in the universe. Quasars, or quasi-stellar objects, are primarily understood as incredibly luminous entities powered by supermassive black holes at their centers. These black holes, typically millions to billions of times more massive than the Sun, pull in surrounding gas and dust. creating a swirling disk that heats up as it spirals inward, emitting tremendous amounts of energy and making quasars some of the brightest objects in the universe. While the prevailing theory attributes the power of quasars to these supermassive black holes, the nature of quasars encompasses more than just the black holes themselves. For instance, the environment surrounding the black hole plays a crucial role. The materials around it can influence how much energy is emitted. If a quasar is actively consuming vast amounts of matter, it will exhibit intense brightness. Conversely, if it's in a less material-rich environment, its luminosity may decrease significantly. Furthermore, quasars can also be impacted by the dynamics of their host galaxies. Interactions with other galaxies can lead to galactic collisions that funnel additional gas toward the black hole, reigniting the quasar's activity. This suggests that while a supermassive black hole is fundamental to a quasar's existence, it is part of a larger, dynamic system that includes the galaxy's structure, the flow of gas, and external cosmic events. Some scientists also explore the possibility that quasars might represent different phases of black hole activity or evolution, indicating that there could be a spectrum of behaviors and characteristics within quasars. This evolving understanding suggests quasars are not merely defined by their black holes, but are instead a complex interplay of cosmic processes, highlighting an ongoing quest for deeper insights into these fascinating astronomical phenomena. A significant portion of the universe remains hidden from our eyes and instruments. While we can observe countless stars, galaxies, and other celestial objects, only a small segment of the total universe is detectable with current technology. Scientists estimate that approximately 95% of the universe consists of dark matter and dark energy, elements that we cannot directly see or measure in conventional ways. Dark matter, which makes up about 25% of the universe, is not the same as the ordinary matter that forms stars and planets. Instead, it interacts with regular matter predominantly through gravity. This means it helps shape the structure of the universe and affects the motion of galaxies, but it does not emit light or energy that can be captured by telescopes. Its presence is inferred from how galaxies spin and cluster together. Then comes dark energy, which is believed to account for about 70% of the universe. This mysterious force is driving the accelerated expansion of the universe, pushing galaxies apart at an increasing pace. Like dark matter, dark energy remains elusive. We cannot observe it directly, but its effects are evident on the grand scale of cosmic structure and evolution. These unseen components raise intriguing questions about the nature of the universe and our place within it, emphasizing that the cosmos is far more complex than what our eyes can perceive. As scientists continue to explore and devise new ways to study the universe, the mysteries of dark matter and dark energy beckon us to delve deeper into the vast, hidden realms that shape everything we see. The laws of physics, as we currently understand them, provide a reliable framework for explaining and predicting natural phenomena. However, the universe is vast and complex, leading some to speculate about phenomena that might defy these established rules. At the heart of this debate lies the recognition that our understanding of physics is always evolving. Take, for instance, the concept of dark energy. This mysterious force appears to be driving the accelerated expansion of the universe, challenging our understanding of gravity and cosmic dynamics. As researchers deepen their studies, they may uncover principles or elements that stretch the boundaries of our laws of physics, revealing new aspects we have yet to grasp fully. Another area ripe for exploration is quantum mechanics, where certain particles can exhibit behavior that seems illogical under traditional physics. The phenomenon of entanglement, where particles remain interconnected regardless of distance, defies our intuitive grasp of space and locality. This suggests a level of complexity in the universe that could lead to new theories that might initially appear to break established laws but would ultimately enhance our understanding. Moreover, hypothetical scenarios like warp drives or time travel present another lens through which we can consider physics' limitations. These concepts, while currently speculative, hint at a reality where the known laws might be bent or modified under the right conditions. Scientists continually assess and integrate new findings, reshaping our understanding of what is possible. Ultimately, the pursuit of knowledge may lead us to phenomena that initially seem to contradict the established laws of physics, but with time and deeper inquiry, we could discover that these new phenomena fit into an even greater framework. The boundaries of physics are continually expanding, driven by discovery and curiosity, highlighting the intricate and sometimes surprising nature of the universe. Certain regions of space are often described as nearly empty due to the vast distances between galaxies and star systems. Imagine the universe as a giant sponge filled with heavy-duty holes. Each hole represents a galaxy bustling with stars, planets, and cosmic activity, while the empty spaces between them are the voids. These voids can stretch for millions of light years, creating vast gaps where little to no matter exists. The formation of these empty regions is rooted in the gravitational nature of matter in the universe. After the Big Bang, the universe was filled with hot gas and energy. Over time, gravity began to group this matter together, forming galaxies and large structures. The areas where matter was less concentrated fell into the remnants of the early universe, developing into these sparsely populated regions. Additionally, cosmic expansion plays a role. As the universe continues to stretch, galaxies are moving away from each other, which further enhances the gaps between them. Some of these voids can be so significant that they contain a strikingly low number of galaxies, creating a sense of emptiness. Even within these seemingly barren spaces, however, there are still faint traces of matter, such as intergalactic gas, dark matter, and even mystery signals. So, while these regions may appear devoid of activity at first glance, they are a testament to the dynamic and ever-evolving structure of the universe. In the vast expanse of the cosmos, the possibility of invisible structures and objects intrigues many. While we rely on visible light to observe celestial phenomena, there are entities that elude our detection because they do not emit, reflect, or absorb light in the way ordinary matter does. One of the most significant examples of this is dark matter. Though it makes up a large portion of the universe's total mass, dark matter doesn't interact with light or other forms of electromagnetic radiation, rendering it invisible to our traditional observational techniques. Instead of being detected directly, its presence is inferred through gravitational effects, how it influences the motion of stars within galaxies and the behavior of galaxy clusters. Additionally, other invisible entities may exist, like certain types of black holes. We often perceive black holes by observing the destruction they cause on surrounding stars or gas. If a black hole is in a region devoid of nearby matter to interact with, it can remain undetected, essentially a silent predator lurking in the cosmic shadows. Moreover, theoretical structures such as primordial black holes could exist, possibly created in the early universe, and they might not reveal themselves through typical means. Following this line of thought, it's plausible to consider other elusive structures or exotic matter that could conceal themselves even more effectively. Furthermore, certain phenomena, such as neutrinos, tiny, nearly massless particles, are incredibly difficult to detect. They stream through space and even through our own bodies without us noticing, often created in the centers of stars. While we see the universe through the light it emits, the idea of invisible structures like dark matter, unobserved black holes, and elusive particles opens a window into a more mysterious landscape. Just because we cannot perceive them doesn't mean they don't play a crucial role in the fabric of the universe. Rather, they are reminders of how much more there is to discover in the cosmic mystery that surrounds us. In the vast tapestry of the universe, voids are expansive, nearly empty regions that exist between clusters of galaxies. Imagine a web where the strands represent galaxies and clusters, and the spaces in between, those expansive gaps, are the voids. These areas can be dramatically larger than typical regions where matter is concentrated, making them some of the largest structures in the universe. Voids emerge as a consequence of the fundamental nature of gravity and the distribution of matter in the early universe. Right after the Big Bang, the universe was a hot, dense soup of particles, but as it began to cool, variations in density formed. Some areas had slightly more matter, while others had less. Over billions of years, the gravitational forces drew matter together into clusters and filaments, while the less dense regions, or voids, were left behind as the universe expanded. The existence of voids provides insights into the universe's overall structure and dark matter. Dark matter, which cannot be seen directly, influences visible matter through gravity. In regions where dark matter is less concentrated, the voids form. These vast areas with fewer galaxies are a visual manifestation of the underlying gravitational dynamics at play. By studying voids, scientists can learn more about the history of cosmic evolution and the mysterious forces that shape our universe. The universe is vast and mysterious, and scientists believe that there are indeed forms of black holes and other compact objects that remain undiscovered. While we typically discuss three main types of black holes, stellar, supermassive, and intermediate, there's a possibility that additional categories exist. For instance, some theories suggest the existence of primordial black holes, which could have formed in the extremely dense environments of the early universe. These black holes would be significantly smaller than those formed from collapsing stars, but could have a range of sizes, potentially accounting for some of the unseen matter in our universe. Furthermore, researchers are actively investigating other compact objects, such as neutron stars, which are extremely dense remnants of supernova explosions. These stars can be exceedingly small, yet possess a mass greater than that of the Sun, presenting unique challenges in our efforts to understand them fully. In addition, exotic objects like quark stars, which might be composed of fundamental particles called quarks, have been theorized but not observed. The pursuit of knowledge in this area is fueled by technological advancements in observational astronomy. Instruments designed to detect gravitational waves have already revolutionized our ability to find and study merging black holes that were previously unobservable. As our capabilities improve, we will likely uncover new types of compact objects and deepen our understanding of their properties and how they influence the fabric of space and time. What's most exciting is the notion that each discovery can lead to new questions and theories, propelling our understanding of the cosmos further into uncharted territory. Discoveries of this scale not only expand our knowledge of black holes, but also could reveal insights into the fundamental nature of the universe itself, including its beginnings, composition, and ultimate fate. Each new find sparks curiosity about what lies beyond our current grasp, reminding us that the universe still holds many secrets waiting to be unveiled. The concept of ancient remnants from failed universes is a fascinating idea, drawing upon theories from both cosmology and philosophy. To imagine this, think about the universe as a grand tapestry woven with countless threads of potential realities. Each thread could represent a different universe, some flourishing while others may not have survived the conditions necessary for existence. If these alternate universes did form, they could potentially create echoes or remnants in our own universe. One scientific way to ponder this is through the existence of certain cosmic structures or anomalies that don't neatly fit within our understanding of cosmic evolution. These could be the faint whispers of a universe that once was. For example, features in the cosmic microwave background radiation, the afterglow of the Big Bang, might contain signatures hinting at interactions or influences from other, now defunct universes. Another avenue of exploration is the multiverse theory, which posits that our universe may be one of many, possibly even infinite in number. In this framework, a universe could undergo a sort of birth, development, and potential demise without interacting with others directly, yet the very structures that arise might offer clues about their origins. Cosmic events like black holes or other high-energy phenomena could serve as metaphors for bridges between realms, hinting at something lost or forgotten. But the evidence for ancient remnants remains speculative. It requires a fusion of profound theoretical insights and observational breakthroughs. As we delve deeper into cosmic exploration, our understanding of the universe's vast history may one day illuminate these enigmas, revealing hints of what once existed beyond the borders of our own reality. This ongoing quest invites us to rethink our views on existence itself and the boundless possibilities that the cosmos may hold. Gravitational wave echoes are intriguing phenomena that emerge in the aftermath of events like the collision of black holes or neutron stars. When these massive objects merge, they create ripples in space-time that travel outward at the speed of light. However, these massive events don't merely produce a single wave. They can also generate a series of echoes, almost like sound reverberating through a canyon. These echoes occur because, after the initial wave passes, the newly formed black hole or neutron star can create additional oscillations. This object can act like a drum, vibrating in response to the energy released from the merger. As this energy disperses in space-time, it creates a distinct pattern of echoes. Scientists have captured these echoes through advanced detectors designed to measure subtle changes in distances across great spans of space. What makes these gravitational wave echoes particularly compelling is their potential to reveal deeper insights about the nature of space-time itself. They hint at unique properties of black holes, such as their shapes and the physics that govern their surfaces, which remain largely mysterious. By examining these echoes, researchers may be able to probe theories of quantum gravity and understand how gravity behaves under extreme conditions, thus revealing new aspects of our universe. The study of gravitational wave echoes represents an exciting frontier in astrophysics. It enables scientists to expand their understanding of how massive objects interact, how space-time can be warped, and ultimately, how the very fabric of the universe is stitched together. Echoes provide a glimpse into the universe's most violent events, allowing us to listen to the echoes of creation while unraveling the mysteries of existence. In the vast cosmos, some star systems stand out due to their extraordinary density and chaotic nature. At the heart of this complexity lies the interplay of gravity, stellar evolution, and the events of cosmic history. Density in star systems can be attributed to the gravitational pull of mass. When a large number of stars are packed into a relatively small space, as seen in globular clusters, the gravitational forces become incredibly strong. This crowding makes it possible for stars to interact more frequently, sometimes resulting in dramatic events like collisions or close encounters. On the flip side, chaos is often a product of the life cycles of stars within these systems. Stars are born, live out their nuclear lives, and ultimately die. The explosive remnants of massive stars, such as supernovae, can trigger further star formation while also dispersing elements throughout the system. These powerful explosions create shockwaves that can compress nearby gas and dust, leading to the birth of new stars amidst the remnants of old ones. This interplay can create a turbulent environment where the gravitational forces vie against the outward push of stellar winds and the energy from explosions, contributing to a sense of chaos. Moreover, the orbits of stars in densely populated regions can become unstable over time. When stars pass close to one another, their mutual gravitational attraction can alter their paths, leading to erratic and unpredictable behaviors. These systems often end up with a mix of tightly bound binaries, pairs of stars that are gravitationally bound to one another, and rogue stars that have been flung away into interstellar space due to dynamic encounters. Another fascinating aspect is the role of black holes. In the densest systems, black holes can form from the remnants of massive stars and can act as gravitational centers, further complicating the dynamics around them. Their presence facilitates a variety of interactions, pushing stars into highly eccentric orbits or even consuming them altogether, creating hotspots of chaotic activity. So, the characteristics of density and chaos in some star systems arise from a combination of gravitational interactions, explosive stellar events, and dynamic evolution, painting a complex portrait of life among the stars in the universe. Neutron stars present an incredible environment where the familiar states of matter we know, solid, liquid, gas, and plasma, undergo extreme transformations. Within these stars, the density is so intense that ordinary atomic structures collapse. At the core of a neutron star, the pressure is so great that electrons and protons are crushed together, leading to the formation of neutrons. This is where the concept of the neutron fluid comes into play, a state of matter where neutrons behave like a liquid that flows freely without the usual atomic constraints. But the story doesn't end there. Scientists theorize that deeper within the core, even more exotic states of matter may exist. One possibility is the formation of quark-gluon plasma, a state thought to occur just moments after the Big Bang. In this state, quarks, elementary particles that combine to form protons and neutrons, exist freely rather than being confined in particles. This means that instead of being bound together in groups, quarks could roam independently in a soup-like state. Moreover, the immense pressure in the core may lead to the emergence of new phases of matter that do not yet have a firm classification. For instance, researchers hypothesize about a state where hyperons, particles composed of different combinations of quarks, could form. This could fundamentally alter the properties of matter in ways that are still being explored. Understanding these potential states of matter not only deepens our comprehension of neutron stars, but also invites us to rethink the very foundations of physics under extreme conditions. Therefore, the cores of neutron stars might be home to uncharted territories of matter, challenging our understanding of the universe itself. Magnetars are a unique type of neutron star, recognized for their incredibly strong magnetic fields, which far exceed those of typical neutron stars or even regular stars. Picture a neutron star as the remnants of a massive star that has exploded in a supernova, leaving behind a core so dense that a sugar cube-sized amount of its material would weigh as much as a mountain on Earth. What sets magnetars apart is their magnetic field, which can be 1,000 trillion times stronger than the strongest magnets you might encounter. This extraordinary magnetic field arises during the star's formation. When a giant star runs out of nuclear fuel and collapses, the conservation of angular momentum causes it to rotate rapidly. As it collapses, the magnetic field gets compressed and intensified. In the case of magnetars, unique processes during the star's life cycle lead to fields that are incredibly potent, possibly stemming from the internal dynamics within the star and the violent events surrounding its birth. These mighty magnetic fields have several effects. For one, they can cause explosive surface events that are detectable as bursts of X-rays and gamma rays, outshining entire galaxies for brief periods. When the magnetic field lines become twisted and unstable, they can release energy in the form of radiation, resulting in spectacular bursts. The immense magnetic forces also affect the surrounding space, pulling in and accelerating particles that create further radiation and heat, presenting a dangerous environment. Magnetars are not just fascinating for their physical properties, they also serve as cosmic laboratories for studying extreme physics. Their existence challenges our understanding of matter, magnetism, and the fundamental forces at play in our universe, illustrating just how diverse and complex the stellar phenomena can be. Indeed, there are stars that can undergo multiple phases of collapse and reforming, and these fascinating processes often involve the life cycles of massive stars. Let's consider a massive star, one that begins its life-burning hydrogen and eventually fuses heavier elements as it evolves. As it exhausts its nuclear fuel, the balance between gravity pulling inward and the outward pressure from nuclear reactions alters dramatically. Initially, when the star depletes its hydrogen, it can swell into a red giant. Later, in a succession of processes, it might fuse helium into carbon or even heavier elements until it reaches iron. At this point, the star is left with an iron core that cannot produce energy through fusion. Unable to support itself against gravitational collapse, the core implodes suddenly. This catastrophic event leads to a supernova, an explosive death for the star that disperses its outer layers into space. However, this dramatic end is often not the conclusion. In some cases, the remnants left behind, such as a neutron star, can experience a second kind of collapse. Should the mass of the neutron star exceed a certain threshold, the pressure can cause it to collapse again, potentially forming a black hole. In this manner, a single stellar body can go through cycles of collapse, resulting in different forms, from a massive star to a neutron star, and finally, potentially a black hole. Moreover, in certain binary systems, two stars can interact in complex ways, leading to phenomena such as periodic mass transfer. One star may strip material from another, which can reignite nuclear fusion processes or contribute to one star's collapse. Thus, the journey of stars is not a simple linear path, but rather a series of transformative events, allowing for the collapse and rebirth into entirely new cosmic entities. Each phase of this celestial dance contributes to the rich tapestry of the universe, influencing the formation of new stars and planets from the remnants left behind. The idea of stars existing that are older than the universe itself invites us to delve into the intricacies of our cosmic timeline. The universe is estimated to be around 13.8 billion years old, based on observations of the oldest light, called cosmic microwave background radiation. A star, however, has a life cycle that can vary significantly depending on its mass and other factors. In this cosmic context, the oldest known stars, often referred to as population 2 stars, are located in ancient globular clusters. These stars formed shortly after the Big Bang, when the first elements coalesced. The faintest among them may have lifespans of tens of billions of years, but they do exist within the limits of the universe's age. Thus, while we can observe extremely ancient stars, none can be conclusively older than the universe itself. Every known star fits within the grand timeline of cosmic history. The challenge comes when new discoveries might reveal previously unaccounted phenomena or objects. For now, our understanding firmly connects the age of stars with the universe, making the notion of stars older than the universe an intriguing thought experiment rather than a reality. Each star tells a story, and understanding their ages enhances our grasp of cosmic evolution, highlighting the unity of everything in existence. Binary stars are captivating cosmic pairs, where two stars orbit around a common center of mass due to their mutual gravitational attraction. Imagine two dancers moving gracefully around each other. As they spin, their gravitational bond keeps them closely tied. These pairs can vary in size, temperature, and brightness, creating a diverse range of binary systems. Some are composed of stars that are similar in characteristics, while others may consist of a large and a small star, adding to the dynamic nature of their interaction. As these stars age, their evolution can lead to dramatic outcomes, one of which is catastrophic merging. This often occurs when one star develops into a red giant and expands significantly. During this phase, it can engulf its companion star. Picture a balloon inflating until it wraps around a nearby object. This is similar to what happens in such a scenario. The gravitational pull and the material exchange between the two stars can cause the smaller star to lose some of its mass to the giant. In other binary systems, particularly those with neutron stars or black holes, the merging process can result from gravitational waves, ripples in space-time created by their orbiting motion. Over time, these waves carry energy away, causing the stars to spiral closer together. Eventually, this tightening orbit can lead to a spectacular collision, unleashing tremendous amounts of energy and sometimes resulting in phenomena like gamma-ray bursts or the creation of supernovae. These events illustrate the fascinating life cycles of stars and the incredible forces at play in these stellar couples, reminding us that even in the cold void of space, dramatic encounters and transformations are constantly occurring. The universe is a wondrous realm where matter takes on forms beyond our everyday experience. Exotic particles, which are fundamental pieces of matter that are not commonly found in our typical understanding of atomic structure, could indeed play a role in the composition of certain celestial bodies. To grasp this concept, consider that conventional stars form primarily from hydrogen and helium, the building blocks of the universe. However, in extreme environments, conditions are ripe for more exotic states to arise. One fascinating possibility lies in the phenomenon of neutron stars, which are incredibly dense remnants of supernova explosions. In these stars, gravity crushes matter so tightly that protons and electrons combine to form neutrons. As the density increases still further, conditions could become suitable for the emergence of strange matter, which is made of strange quarks, along with the usual up and down quarks that form neutrons and protons. Theoretically, a star composed entirely of strange matter might even be more stable than typical matter at such extreme densities. Further still, researchers have speculated about quark stars, which could consist of free quarks, the very building blocks of protons and neutrons, instead of being bound into traditional atomic structures. These exotic stars would exhibit unique properties, such as different cooling rates and emissions, distinguishing them from their more familiar counterparts. Despite these intriguing theories, no definitive evidence has been found for stars entirely made of exotic particles thus far. The quest to understand the nature of these stars involves delving into the realms of astrophysics and particle physics, pushing the boundaries of our knowledge. The study of such stars not only presents a scientific challenge, but also offers a glimpse into the vast complexity of the cosmos, where familiar rules of matter can bend and transform in the most extraordinary ways. The search for a planet with conditions entirely opposite to those found on Earth is a fascinating and daunting pursuit. To envision such a place, we can think about various environmental factors that define our planet, including temperature, atmospheric composition, pressure, and even gravity. Let's start with temperature. Earth's average climate is temperate, with diverse ecosystems thriving in moderate conditions. Now, imagine a planet that exists in a realm of extremes, where temperatures soar to scorching levels or plunge to bone-chilling lows. This could create a world where liquid water, essential to life as we know it, is either vaporized or frozen solid. Next, we can consider atmospheric conditions. Earth's atmosphere is rich in oxygen and nitrogen, crucial for supporting life. In contrast, an opposite planet might possess a thick atmosphere laden with toxic gases, such as sulfur dioxide or methane, which could create a hostile environment for respiration and photosynthesis. The atmospheric pressure might also differ greatly, potentially crushing anything resembling Earth's organisms, or, conversely, leading to a near vacuum that would leave life vulnerable to cosmic radiation. We should also address gravity. Earth's gravitational pull allows for a stable environment where life can thrive. In imagining a planet with the opposite gravitational force, we might picture a world with significantly weaker or stronger gravity. Too weak, and structures could be flimsy, while too strong could compress everything into dense forms, making the environment unsuitable for life as we understand it. In addition to these factors, we must think about the planet's distance from its star. An Earth-like distance encourages a delicate balance conducive to liquid water. However, a planet positioned too close would be subjected to relentless solar radiation and unending heat, while one too far might be a frozen wasteland, devoid of warmth and light. While planets with extreme conditions do exist, such as the scorching world of Venus or the frigid climate of Mars, finding one that is the complete antithesis of Earth, a place where the laws of nature unfold in stark contrast to what we know, is an ongoing challenge. Astronomers are constantly seeking out exoplanets with different characteristics, and while we may not have yet found a perfect opposite, the universe is vast and full of possibilities, leaving room for remarkable discoveries. Yes, there are indeed planets that might not orbit stars in the traditional sense. These unique worlds, often referred to as rogue planets, may float freely through space, seemingly unanchored to any celestial body. Rogue planets can arise from a variety of processes. For instance, they might form in a protoplanetary disk around a young star, but be ejected from their systems due to gravitational interactions with other planets or nearby stars, leaving them drifting alone in the vastness of space. Additionally, it's conceivable that some planets could orbit black holes or neutron stars, extremely dense remnants of massive stars. In such cases, the strong gravitational pull of these small yet powerful objects could capture a planet that strayed too close, pulling it into orbit. However, these orbits would be quite different from those around regular stars due to the intense gravitational fields and the unique characteristics of such compact objects. For rogue planets or planets orbiting black holes, the environment is harsh. The lack of a nearby star means they are unlikely to have the warmth or light that life as we know it requires. In contrast, if a planet were to orbit a neutron star, which is a very dense body resulting from a supernova, it would face extreme radiation and potentially violent gravitational forces. Thus, while these planets may not orbit a star like our Sun, their existence hints at the astonishing diversity of planetary systems and the many ways celestial bodies can interact across the cosmos. As of 2024, astronomers have made significant strides in identifying exoplanets that share characteristics with Earth, igniting excitement about the potential for life beyond our home planet. These Earth-like exoplanets are found in what is termed the habitable zone, a region around a star where conditions could allow for liquid water, a key ingredient for life. Among the most intriguing discoveries is a planet roughly similar in size to Earth, situated around a star not far from our solar system. This exoplanet orbits within its star's habitable zone, meaning temperatures could sustain liquid water on its surface. Scientists believe that the presence of water dramatically increases the likelihood of finding life as we know it. Moreover, the composition of its atmosphere suggests it may have clouds and even be capable of climatic conditions similar to those on Earth. Another notable candidate has been identified with a rocky surface, atmospheric readings hinting at the possibility of an Earth-like climate. Its orbit is stable, and preliminary studies suggest it experiences seasonality akin to our planet, potentially nurturing diverse environments. Then there's an alluring exoplanet that exhibits signs of geological activity, indicating that it might have volcanoes. Such features can contribute to a dynamic atmosphere, essential for weather patterns and cycles that could support life. Each of these discoveries reinforces the idea that we are not alone in the cosmos. Further study will delve deep into their atmospheres and compositions, searching for biosignatures, substances or phenomena that might indicate the presence of life. In doing so, astronomers inch closer to answering one of humanity's deepest questions. Are we the only ones in this vast universe? The year 2024 stands as a testament to our blossoming understanding of the cosmos and the possibilities it holds. When we think about life beyond Earth, it is crucial to recognize that it could take forms beyond our wildest imagination. On our planet, life thrives in many environments, from the deep ocean trenches to the scorching deserts. This adaptability has led scientists to wonder about the conditions that could support life elsewhere in the universe. Many alien worlds are found in extreme conditions. For instance, some exoplanets orbiting close to their stars may experience intense heat, while others might be frozen in deep space darkness. Life could exist in these extreme environments, possibly utilizing biochemistries that differ drastically from our own. Picture organisms that might extract energy from chemical processes instead of sunlight, akin to the extremophiles we find in Earth's harshest landscapes. The concept of life adapting to various surroundings suggests that a planet's atmosphere, surface conditions, and available resources will dictate what forms life takes. It's entirely plausible that alien life forms could be based on entirely different elements than carbon, which is fundamental to Earth life. For example, scientists have speculated about life based on silicon, a common element in the cosmos, which may allow for surprisingly distinct biochemical processes. Imagine creatures that can tolerate high radiation levels or survive in environments with pressures far beyond what we can endure. Such life forms could emerge in liquid methane oceans, thrive in gaseous atmospheres rich with unknown chemicals, or exist in subterranean habitats beneath a planet's surface, shielded from violent environments above. Thus, the potential variety of alien life is limited only by the universe's conditions. As we continue to explore, our understanding of what life could be expands. This pursuit not only broadens our horizons, but also raises profound questions about our existence, echoing the core inquiry of humanity. Are we alone, or are there beings out there, different from us in ways we have yet to imagine? Tidally locked planets are fascinating celestial bodies that are in synchrony with their star, meaning one side always faces the star while the other side remains in perpetual darkness. Imagine a spinning top that slows down until it can no longer turn. Eventually, it aligns perfectly, showing the same face to its surface. On a tidally locked planet, the side facing the star experiences constant daylight, with heat and light pouring in continuously. In contrast, the dark side is shrouded in eternal night and can be extremely cold. This unique configuration presents distinct environments on each side. On the sunlit side, temperatures could soar and winds might whip across the landscape, creating a dynamic atmosphere. The dark side, however, could feature frigid conditions and icy terrains. Life on such planets would face significant challenges, but also opportunities for remarkable adaptation. Organisms might evolve to thrive in the constant light or without sunlight entirely. Photosynthetic life forms could develop sensitive mechanisms to optimize energy capture during the prolonged day. Other species might migrate between the two extremes, creating a fascinating dynamic ecosystem tied to light and dark cycles. It's also possible for life forms to exist along the twilight zone, the narrow region at the edge where light gradually fades into darkness. This region might serve as a rich habitat, balancing the extremes of heat and cold. Creatures may adapt physically and behaviorally to these extremes. For example, species residing on the hot side might evolve reflective surfaces to deflect intense sunlight or burrow underground to escape the heat. Meanwhile, life forms on the dark side may develop excellent thermal insulation or rely on unique forms of energy, such as chemosynthesis, which harnesses chemicals from their environment rather than sunlight. While tidally locked planets offer unique challenges for life, the potential for adaptation is vast, leading to the possibility of a diverse and resilient biosphere. Dark matter halos are vast, invisible structures that surround galaxies and are believed to make up a significant portion of the universe's total mass. Despite being invisible, dark matter exerts a powerful gravitational influence, helping to hold galaxies together and affecting their movement within the cosmos. Within these halos, there is ongoing research and curiosity about the possibility of hidden planets or stars. While dark matter itself does not interact with normal matter in ways we can directly observe, its gravitational properties can influence visible matter, including celestial bodies. In theory, if ordinary matter, like planets and stars, was captured within a dark matter halo, it might not be easily detected, especially if such objects were far away from the stars or galaxies they might otherwise be associated with. Some scientists propose that the gravitational pull from these dark matter structures could create environments suitable for the formation of celestial bodies. In a sense, the gravitational framework established by dark matter may help in accumulating gas and dust, the building blocks of stars and planets, without itself being visible. However, any hidden bodies within dark matter halos would likely be isolated and hard to detect, as they wouldn't emit light in the way we typically observe celestial objects. The idea of hidden planets or stars within these halos opens intriguing possibilities about the nature of the universe and the perhaps uncharted territories where matter exists. It also emphasizes that our understanding of dark matter and its interactions with ordinary matter is still evolving, highlighting an exciting frontier in astrophysics where new discoveries are waiting to be uncovered. Imagining advanced civilizations in distant galaxies opens a realm of possibilities shaped by diverse environments and unique evolutionary paths. First, consider a planet orbiting a star that provides just the right conditions for life, similar to Earth's situation with a stable climate and ample liquid water. This civilization might develop technology using resources abundant in its environment, such as metals for building or energy sources that could differ dramatically from our reliance on fossil fuels. In another scenario, a civilization might thrive on a gas giant. Here, life could be floating in the dense atmosphere, perhaps evolving to harness energy from electrical storms. Instead of building cities, these beings could create vast networks of drifting structures, utilizing buoyancy and atmospheric currents to navigate their world. Their technology and society would revolve around harnessing the raw power of their environment, leading to very different cultural values and scientific pursuits. Intelligent life could also emerge in extreme environments, such as icy worlds or near-extreme volcanic activity. These beings might develop unique adaptations, perhaps relying on bioluminescence or thermophilic processes. Their approach to technology may focus on bioengineering, creating symbiotic relationships with their surroundings, thus fostering a sustainable coexistence rather than extraction. Communication methods could vary widely among these civilizations. They might utilize sound, light, or even chemical signals, leading to complex languages that are beyond our comprehension. Social structures could range from community-based organizations to hive-like collectives, fundamentally changing the way these beings interact, govern, and innovate. Ultimately, while their physical forms and technologies could be vastly different, their pursuit of knowledge, survival, and perhaps even connection to others could echo the themes that are familiar to us. Each of these advanced civilizations, shaped by their unique galactic circumstances, would embody a distinct reflection of the wonders of life as it might exist beyond the confines of our own planet. Indeed, certain space phenomena are so vast that they're beyond our ability to observe in their entirety. One prime example is the universe itself. While we can observe a portion of it through telescopes, our view is limited by the speed of light and the age of the universe. This means we can only see objects that are within a certain distance from us. Beyond that, light from more distant regions has not yet had time to reach us. The observable universe is immense, but it represents just a fraction of the entire cosmos, which may continue indefinitely. Galaxies themselves can be incredibly large, spanning hundreds of thousands of light-years across. Even if we focus on one, we are only able to capture images of its parts, leaving the whole structure partially unseen. Not to mention, some galaxies are part of larger formations, such as clusters, which can contain hundreds of galaxies sprawling across vast distances. Another captivating phenomenon is the cosmic web, which describes the large-scale structure of the universe. This web consists of galaxy filaments and clusters linked by vast voids. The intricate patterns of the cosmic web are so extensive that we can only study sections of it, leaving much of this grand tapestry hidden from our complete view. Additionally, massive structures like superclusters, the largest known structures in the universe containing groups of galaxies, pose similar challenges. Their sheer size makes it difficult to capture their entirety in one observation, and combinations of these superclusters can stretch further than we can currently observe. While our technology and understanding of the universe have advanced remarkably, the limitations of light travel, immense distances, and the sheer size of cosmic structures mean that vast portions of space phenomena remain tantalizingly out of reach. Each glimpse we get paints just a partial picture of the unimaginable scale of the universe. Understanding what lies within a singularity, the core of a black hole, poses one of the most profound mysteries in astrophysics. A singularity is defined as a point where gravitational forces compress matter to an infinitely small space, resulting in infinite density, and curiously, where the known rules of physics seem to break down. This extreme condition challenges our understanding because the very laws that describe the universe, namely general relativity and quantum mechanics, struggle to coexist in such an environment. To envision this, think of a fabric stretched across a framework representing the fabric of space-time. When a black hole forms, it dramatically warps that fabric, creating a deep well. At the bottom, the singularity awaits, hidden from view and surrounded by an event horizon, a boundary beyond which no information can escape. Once anything crosses this threshold, it becomes impossible to retrieve information about it, leaving the singularity shrouded in mystery. Scientists are actively exploring theories that might illuminate some insights into this enigma. One approach involves attempts to unify gravity with quantum mechanics through theories like string theory or loop quantum gravity. These frameworks seek to explain phenomena in a way that might provide glimpses into the behavior at the center of a black hole. However, regardless of advancements in theoretical physics, the inherent nature of a singularity suggests that it could remain fundamentally inaccessible to observation. The extreme conditions create an environment where normal concepts of space and time cease to apply. Thus, while we may simulate conditions and develop theories about what occurs near a singularity, truly comprehending its inner workings might always elude us, reinforcing the awesomeness and mystery of our universe. The concept of regions in the universe where physical laws differ fundamentally is a captivating one. It often leads us to ponder the nature of reality itself. According to our best understanding of physics, particularly the frameworks that describe forces and particles, the laws we observe, like gravity, electromagnetism, and the behavior of subatomic particles, are consistent throughout what we know as the observable universe. However, some theories, particularly in the realm of cosmology and string theory, suggest the possibility of other universes existing beyond our own, sometimes referred to as the multiverse. In such scenarios, each universe within this multiverse might possess its own distinct set of physical laws. For instance, in one universe, gravity could be significantly stronger or weaker, or the fundamental particles that make up matter might behave differently. If these universes exist, they would be vastly separated from ours. For instance, they could be situated in dimensions we cannot currently observe or interact with. In addition, some scientific hypotheses propose that throughout the early moments of our own universe, different regions may have experienced different physical conditions due to fluctuations in energy. Nonetheless, according to our observations and experiments, we have yet to find definitive evidence supporting the existence of entirely different physical laws in any part of our known universe. The laws we apply in astrophysics, quantum mechanics, and relativity remain pivotal in explaining the behavior of everything we can observe within our cosmic horizon. Yet, the adventure of cosmic exploration and the quest for knowledge keeps us intrigued, reminding us that the universe is far more complex and mysterious than we can fully grasp. The idea that different laws could manifest in distant realms invites both scientific curiosity and philosophical reflection about the nature of existence itself. This past year has been a thrilling chapter for comet discovery, with several unexpected finds reshaping our understanding of these icy wanderers. One standout was a comet that exhibited unusual brightness and an unexpected tail. Instead of the typical straight tail, this comet's trail twisted and curved dramatically, hinting at complex interactions with solar winds and cosmic particles. Such a structure suggests that the materials ejected from the comet's surface were reacting in ways we had not fully understood before. Another surprise came from a comet that was discovered in a part of the sky where astronomers had not expected to find one. This finding challenges our previous assumptions about the distribution of comets in the solar system, suggesting that there might be many more undiscovered objects lurking in the shadows. The surprising aspect of this discovery was not just its location, but also its unusually elongated orbit, which could provide clues about the comet's history and origin. Perhaps the most astonishing revelation involved a comet that showed signs of having an atmosphere, or coma, much larger than typical for its size. Scientists were fascinated by the gas and dust expanding from its nucleus. This indicates something unique about its composition or activity. A comet with a significant coma suggests it could be more geologically active than previously considered, hinting at processes we might find intriguing in planetary science. These unexpected discoveries remind us that the universe is full of surprises. Each comet can tell us a new story about the building blocks of our solar system and the dynamic forces at play. As researchers continue to explore these phenomena, we can expect our comprehension of these celestial objects to evolve, revealing deeper secrets of the cosmos. Recent observations of asteroids have revealed some intriguing behaviors that challenge our understanding of these rocky bodies. One particularly fascinating aspect is the phenomenon of active asteroids. Unlike typical asteroids, which are relatively inert, active asteroids display comet-like characteristics, such as developing tails or ejecting dust when they approach the Sun. This behavior suggests that they may harbor volatile materials beneath their surface, which heat up as they get closer to our star, causing the release of gas and particles. For example, a few of these asteroids have shown sudden changes in brightness, indicating that material is being expelled, a process that creates a visible tail or cloud. This suggests that their internal dynamics can be quite complex and may be driven by sublimation, the transformation of solid materials into gas as they warm. Additionally, advancements in observational technology have captured asteroids exhibiting unexpected rotational behaviors. Some are spinning much faster than previously thought possible, leading scientists to consider how these rapid rotations affect their structures and stability. The shape of an asteroid can change, becoming elongated or even irregular, as centrifugal forces influence the distribution of mass. These new insights into asteroid behavior not only enhance our understanding of these celestial objects, but also raise crucial questions about their role in the broader context of our solar system. With each new discovery, we deepen our appreciation for the dynamic nature of asteroids and their potential interactions with planets, including Earth. The most significant meteor shower event in 2024 was the Perseids, which captivated observers with a dazzling display. The Perseids occur annually as Earth passes through the debris left behind by the comet Swift-Tuttle. As the Earth orbits the Sun, it intersects the trail of tiny particles that the comet sheds during its journey. When these remnants, which are often no larger than a grain of dust, collide with Earth's atmosphere at high speeds, they ignite due to friction, creating bright streaks of light, what we know as meteors. The Perseids are particularly renowned for their intensity because many of the particles are relatively large compared to those in other meteor showers, resulting in spectacular fireballs that can light up the night sky. In 2024, favorable conditions, such as a dark night sky with minimal light pollution and a timing coinciding with the peak of the shower, allowed for an extraordinary view. This combination offered stargazers around the world an exceptional opportunity to witness this celestial phenomenon, reminding us of the dynamic and ever-changing nature of our universe. Asteroids, scattered throughout our solar system, have long intrigued scientists due to their ancient composition and potential to reveal the secrets of planetary formation. However, if we consider the idea of asteroids functioning as natural interstellar probes, the concept requires a bit of imaginative thinking. Picture an asteroid, hurled from the depths of a distant solar system, breaking free of its gravitational tether and embarking on a solitary journey through the vast expanse of space. These fragments of rock and metal could carry information from their home systems, encapsulating data about their origins and the conditions in which they formed. While they lack the sophisticated instruments of human-made probes, they still possess inherent characteristics that provide insights into their environments. As they drift through space, these asteroids could potentially interact with the materials from other star systems. For instance, as they encounter interstellar gas and dust over millions of years, they might collect samples of those cosmic materials. This process could offer a glimpse into the molecular makeup of other stellar neighborhoods, giving us clues about star and planet formation elsewhere. Despite this fascinating imagery, the actual chances of one of these asteroids making meaningful contact with our own solar system are slim. The distances between stars are mind-bogglingly vast, and the odds of an asteroid wandering directly into our path are exceedingly low. However, if we were to discover such an asteroid, its journey through space could share a narrative of cosmic exploration, essentially serving as a time capsule from its origin. The example of Oumuamua, an object that passed through our solar system, highlights how an interstellar visitor can provoke interest. Though it was quick and enigmatic, it sparked discussions on the nature of these celestial wanderers and their potential to inform us about the universe beyond our solar neighborhood. Such encounters hold immense potential, and should they occur more frequently, we could view these asteroids as wandering probes, carrying the tales of their homeworlds across the dark tapestry of space. Recent discoveries in the search for exoplanets have unveiled some surprising atmospheres that challenge our understanding of planetary formation and dynamics. One standout example is a planet designated as a hot Jupiter, which encircles its star at a remarkably close distance. Instead of the expected atmosphere rich in hydrogen and helium, observations revealed that it contains unusual elements such as iron and magnesium. This unexpected composition hints at complex processes during the planet's formation, suggesting it could have retained materials that typically dissipate under such intense heat. Another intriguing case involves a planet classified as a super-Earth, which appears to have developed a thick, steamy atmosphere rich in water vapor. While astronomers anticipated that such planets might exhibit rocky surfaces with thinner atmospheres, this discovery indicates that they can acquire voluminous gas layers, potentially creating conditions conducive to climate and weather patterns unlike anything seen on Earth. Moreover, researchers have also detected signs of carbon-bearing molecules in the atmosphere of another exoplanet, raising the possibility of chemical reactions similar to those found on Earth. This unexpected finding creates excitement around the potential for more nuanced atmospheric chemistry on these distant worlds, possibly suggesting varied origins and evolutionary paths. These discoveries not only broaden our knowledge of the diversity among exoplanet atmospheres, but also encourage scientists to reevaluate existing theories about how planets evolve. Each new finding reshapes the fascinating narrative of cosmic diversity as we continue exploring the vast, intricate realm beyond our solar system. Stars, particularly young ones, often display stunning jets of energy that can stretch across vast distances in space, sometimes reaching light years. These jets are the result of complex interactions that take place in a star's formative stages, primarily related to how it forms and accumulates material. During a star's formation, it begins as a massive cloud of gas and dust called a stellar nebula. As gravity pulls this material inward, it starts to spin and condense into a dense object at the center. This process also creates an accretion disk, a flat, rotating disk of material surrounding the protostar. As matter from this disk spirals inward towards the star, it heats up due to friction and gravitational forces, reaching incredibly high temperatures. However, not all the material feeds into the star. Some of it is ejected outward at incredible speeds along the star's rotational axis, forming the energetic jets we observe. These jets are composed primarily of charged particles and radiation, propelled by magnetic fields generated in the swirling gas. As matter is expelled from the star, it interacts with the surrounding interstellar medium, creating shock waves that can glow brightly in various wavelengths of light. The process behind the jets is linked to angular momentum, the tendency of a rotating body to maintain its spin. As the star spins, this momentum helps channel some of the falling material into tightly focused jets, leading to an impressive cosmic display. These jets can continue to emit energy long after the star has formed, influencing its environment and sometimes even triggering new star formation in nearby regions. The sight of these jets is a magnificent reminder of the dynamic and ever-evolving nature of the universe, showcasing the dramatic life cycles of stars and their influential role in shaping the cosmos. In the vastness of space, the behavior of stars and planets can indeed sometimes catch us by surprise, leading scientists to suggest the presence of unknown forces at play. Galaxies swirl in delicate formations, and within them, stars dance in orbits governed by gravity. However, when we observe these celestial bodies, we sometimes notice one star veering off its expected trajectory, or a planet wobbling in a way that standard gravitational laws can't quite explain. One scenario involves the gravitational influence of unseen mass, often referred to as dark matter. Though we can't see it, dark matter makes up a large portion of the universe's mass. Its presence can subtly alter the motion of galaxies, leading to observable anomalies. It's as if there's an invisible hand guiding these cosmic dancers, pushing and pulling them in unexpected ways. Another exciting possibility comes from the realm of exoplanets, planets outside our solar system. Many of these distant worlds have been found in systems with complex dynamics, where their gravitational interactions can lead to erratic changes in their paths or even in their atmospheres. For instance, a planet could be partially dislodged from its orbit due to the gravitational tug of a nearby star or a massive neighbor, illustrating the chaotic beauty of our universe. Moreover, there are hints of phenomena that we have yet to fully understand, such as the potential existence of massive, isolated celestial objects that could exert force without being detected directly. These could be rogue planets, neutron stars, or other enigmatic structures that create ripples in spacetime, influencing their environments in unforeseen ways. Observational astronomy continually refines our understanding, and it's this quest for knowledge that leads us to scrutinize the night sky for behaviors that seem beyond the simple explanations provided by gravity alone. Every discovery could open up a new chapter in our understanding of cosmic mechanics, guiding us to reassess what we think we know about the universe and its myriad forces. Traditionally, we think of black holes as entities that consume everything that comes too close, trapping matter and light within their grasp. However, recent research has unveiled a fascinating twist to this expectation. Under certain conditions, black holes can indeed eject matter into space. This phenomenon occurs primarily in what are known as supermassive black holes, which reside at the centers of galaxies. Around these black holes, there exists an accretion disk, a swirling collection of gas, dust, and debris that spirals inward. As matter falls toward the black hole, it heats up significantly and builds enormous pressure, sometimes leading to explosive outflows. In specific scenarios, these outflows manifest as powerful jets. Imagine a garden hose that, when kinked, suddenly bursts free, sending a stream of water with great force. In a similar fashion, certain particles, driven by magnetic fields and immense energy, can be propelled away at speeds nearing that of light. These jets can extend far into space, sometimes reaching distances that outstrip the size of the galaxy itself. They carry not just gas and dust, but also carry heavy elements forged within the black hole's vicinity. This ejection activity has profound implications for the surrounding environment, influencing star formation and galactic evolution. The energy released can reshape nearby regions, dictating how matter in the galaxy behaves, while also potentially affecting the formation of new stars. This surprising ability of black holes to not only consume, but also to release matter adds an intriguing layer to our understanding of these cosmic giants, underscoring their role not merely as vacuum cleaners of the universe, but also as active participants in the cosmic cycle of matter and energy. Galaxies are grand, swirling collections of stars, gas, and dark matter, each rotating at an incredible speed. However, sometimes astronomers notice that certain galaxies slow down in their rotation unexpectedly, and this phenomenon raises intriguing questions about the dynamics of the universe. One major factor contributing to this slowdown is the interaction between galaxies. When two galaxies encounter each other, their gravitational forces can have dramatic effects. Imagine two dancers twirling closely. As they approach each other, their movements can alter. Likewise, when galaxies collide or pass by one another, they can exchange momentum and energy, leading to a redistribution of material within each galaxy. This interaction can induce drag on the outer parts of a galaxy, causing its rotation to slow down. Another factor at play is the process of star formation. As gas clouds within a galaxy collapse to form new stars, the distribution of mass changes. If a significant amount of gas is converted into dense stars, the remaining material may not rotate as efficiently. This transformation alters the overall distribution of mass and influences how the galaxy rotates. Essentially, the galaxy's structure is reshaped, impacting its rotational dynamics. Additionally, the presence of dark matter plays a crucial role. Dark matter, which cannot be seen directly, has a significant gravitational influence on visible matter. If dark matter is redistributed because of interactions or dynamic changes in the galaxy, it can also affect the rotation rate. The loss or rearrangement of dark matter can lead to a decline in the gripping force that sustains high-speed rotation. Lastly, environmental factors such as the galaxy's position within a cluster can create a drag effect on its rotational speed. Galaxies in dense clusters can experience gravitational effects from surrounding galaxies, leading to what's often termed tidal interactions, which can slow down their rotation. The slowdown of a galaxy's rotation results from a combination of gravitational interactions during collisions, changes in mass distribution due to star formation, the influence of dark matter, and environmental dynamics within galaxy clusters. Each of these factors contributes to this complex dance of cosmic forces, reminding us of the ever-evolving nature of the universe. The universe is an intricate tapestry, woven together by various forces that create both order and chaos. Evidence of chaotic forces shaping the cosmos can be found in many forms, revealing how they influence the structure and evolution of galaxies, stars, and even entire clusters of matter. One striking example is in the interactions of galaxies. When two galaxies come close enough to each other, their gravitational pull can lead to a spectacular chaos of cosmic proportions. These interactions can cause unexpected formations, such as tidal tails, where matter is distorted and stretched, showing the unpredictable dance of gravity at work. Additionally, the birth of stars can also display chaotic characteristics. In the dense clouds of gas and dust, the process of star formation can be influenced by turbulence within the cloud. This can lead to areas of dense material collapsing under their own gravity, while other regions remain diffuse. The resultant interplay can create a patchwork of newly formed stars and stellar remnants, each with its unique path and destiny. On a larger scale, the phenomenon of cosmic structures also hints at chaotic forces. The universe itself is a dynamic entity, subject to various influences like dark energy and dark matter. As these invisible components tug and pull at the fabric of space, they contribute to the clustering of galaxies, forming filaments and voids in what is known as the cosmic web. The patterns emerge from the chaotic nature of these forces, demonstrating how they shape the grand structure of the universe over eons. The evidence of chaotic forces across the cosmos isn't merely a concept, it is an observable reality. From the collision of galaxies to the birth of stars and the formation of cosmic structures, these forces illustrate the unpredictable yet fascinating nature of our universe, continually shaping its evolution in ways we are beginning to grasp but have yet to fully understand. In the vast tapestry of the universe, spontaneous giant phenomena can indeed arise under the right conditions. For example, consider the formation of massive clouds of gas and dust, often referred to as nebulae. These clouds may coalesce due to gravitational forces acting on them, drawing in surrounding material over time. When the density of this gas and dust reaches a critical point, it can ignite a chain reaction that results in the birth of new stars. Furthermore, celestial events like supernovae, the explosive deaths of massive stars, can also occur seemingly out of nowhere. As a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. This dramatic transformation happens quickly in cosmic terms, resulting in an explosion that disperses elements across space, seeding new stars and planets in the process. Another intriguing phenomenon that appears suddenly is the emergence of pulsars. These highly magnetized, rotating neutron stars emit beams of radiation. When conditions are just right, a supernova can leave behind a neutron star capable of becoming a pulsar. This transformation can happen rapidly, creating intense bursts of energy. Lastly, theories have proposed the existence of spontaneous black holes that might form not just from dying stars, but potentially from dense regions of matter collapsing under their own weight. While this conjecture remains largely theoretical, it illustrates how the cosmos is continually evolving, with new structures sometimes forming in unexpected ways. The universe thrives on spontaneity, driven by gravitational forces, stellar life cycles, and the complex interactions of cosmic materials. Each instance of creation speaks to the dynamic and ever-changing nature of space, where what seems stable can suddenly shift, giving birth to phenomena of monumental scale. In 2024, scientists experienced moments that reshaped their understanding of the universe, igniting excitement and curiosity across the global research community. One of the most astonishing breakthroughs involved the discovery of a new exoplanet located in what is termed the habitable zone of its star. This zone is significant because it's the area where conditions might be right for liquid water to exist, a critical ingredient for life as we know it. The presence of water vapor in the planet's atmosphere was detected, stirring imaginations and sparking discussions about the possibility of extraterrestrial life. Another surprising discovery came from deep space observations, where researchers noted unusual cosmic signals indicative of phenomena not previously understood. These signals led astronomers to speculate about new astrophysical processes that could change our comprehension of events like supernova explosions and black holes. The excitement stemmed not just from the findings themselves, but also from the implications they held for fundamental physics and our knowledge of how the universe evolves. In the realm of particle physics, scientists unveiled results from experiments that suggested the existence of an elusive particle believed to carry a form of dark matter. This was particularly remarkable because dark matter constitutes a vast majority of the universe's mass, yet remains largely mysterious. The potential to finally elucidate its nature sent waves of enthusiasm through the scientific community, prompting collaborative efforts and new research initiatives aimed at understanding the role dark matter plays in cosmic structure formation. These discoveries triggered a flurry of reactions among scientists, extending beyond mere astonishment. Researchers often expressed feelings of exhilaration accompanied by a sense of urgency to follow up on these findings. Conferences and discussions rapidly focused on these new possibilities, marking a significant shift in research priorities. The thrill of the unknown, coupled with the promise of potentially rewriting textbooks, united scientists across various disciplines in pursuit of deeper understanding. The year became a defining moment in scientific history, showcasing humanity's enduring quest to peer into the depths of the cosmos and unlock its many secrets. This year has indeed seen several intriguing discoveries that challenge our understanding of the universe and prompt scientists to reevaluate existing theories. One significant finding involves the detection of unusual gravitational waves, which are ripples in the fabric of space-time caused by massive cosmic events, such as colliding black holes or neutron stars. These waves carried signatures that were unexpected, suggesting new interactions or properties of these celestial bodies that previous models did not account for. In addition, researchers analyzing deep space images from powerful telescopes have reported anomalies in the behavior of distant galaxies. Observations indicate that some galaxies are rotating in ways that contradict our current understanding of dark matter's influence. Dark matter, an invisible substance thought to make up a substantial portion of the universe's mass, has always been expected to influence galactic rotation in specific patterns. This new evidence could imply either the existence of new forces at work or necessitate adjustments in the perception of dark matter itself. Furthermore, the exploration of extreme environments, like those found in deep space, has unveiled unexpected chemical compounds and reactions that challenge theories about how these materials form and evolve. These findings might lead to revisions in theories about star formation and the life cycle of cosmic materials. Together, these discoveries demonstrate that our understanding of the cosmos is continually evolving. Each new piece of evidence serves not only to deepen our knowledge, but also to remind us of the complexities of the universe surrounding us, urging scientists to remain open to new ideas and explanations. The quest for understanding is ongoing, and who knows what other surprises the universe has in store. The universe is vast and largely unexplored, so the discovery of entirely new categories of celestial objects is certainly within the realm of possibility. Scientists are continuously pushing the boundaries of our understanding, often challenging previous classifications and discovering phenomena that defy existing knowledge. Imagine the early observations of pulsars, which were initially thought to be signals from extraterrestrial civilizations, but turned out to be rapidly rotating neutron stars with unique properties. New telescopes and observational techniques are enhancing our ability to explore the cosmos. For instance, advancements in technology allow us to detect faint objects that were previously overlooked. This could lead to the identification of unusual objects that fall outside current categories, perhaps something not yet imagined, like exotic planetary systems or phenomena resulting from new physical processes that are not well understood. Moreover, the realm of theoretical physics is rich with potential discoveries. Concepts such as dark matter and dark energy suggest there are aspects of the universe still shrouded in mystery. Discovering an entirely new category of celestial object might involve understanding these enigmatic components and how they interact with visible matter. As our knowledge expands, so too does the possibility of encountering celestial objects unlike anything we've seen before. Every exploration mission to distant worlds, every advance in computational astrophysics could unveil surprising new findings. Just as comets and asteroids expanded our view of the solar system, future discoveries could redefine how we classify celestial entities, showcasing the dynamic and ever-evolving nature of the universe. With each new telescope launched and every mission launched to explore space, we edge closer to revealing the surprising secrets held by the cosmos, including the potential for altogether new celestial categories. In the realm of space exploration, scientists often encounter phenomena that challenge our understanding of the universe, leading to some truly fascinating and bold theories. One of the most captivating is the concept of dark matter. While we can observe the effects of gravity on galaxies, many characteristics suggest there is something unseen, something that doesn't emit light or energy. Scientists theorize that dark matter composes a significant portion of the universe, possibly acting like an invisible scaffold, shaping galaxies and influencing their structure. Despite extensive searches, it remains elusive, prompting speculation about its nature and origins. Another intriguing theory revolves around the idea of parallel universes. Some physicists propose that what we perceive as our universe might be just one of many. These alternate realities could have different physical laws, constants, or even entirely different timelines. If true, it raises questions about our understanding of existence itself. What if there are infinite versions of ourselves living out varying destinies in these parallel realms? Then there's the mystery of fast radio bursts, brief, intense bursts of radio energy originating from deep space. These fleeting signals have puzzled scientists since their discovery. While some speculate they are signals from advanced extraterrestrial civilizations, others suggest more natural explanations, such as colliding neutron stars or magnetars, which are highly magnetic and dense remnants of collapsed stars. The true origin of these bursts remains one of the great unanswered questions in astrophysics. Lastly, scientists are also delving into the enigmatic phenomena of cosmic inflation. This theory suggests that shortly after the Big Bang, the universe expanded exponentially in an unimaginably brief moment. This rapid growth helps explain the uniformity we observe in the universe today. However, understanding what triggered this inflation, and how it fits into our current models of physics remains a challenge. These theories embody the spirit of scientific inquiry, pushing the boundaries of our understanding and inviting us to explore the unknown. Each discovery leads to new questions, keeping our quest for knowledge alive and exciting. Dyson spheres, conceptualized by physicist Freeman Dyson, represent a fascinating idea for advanced civilizations looking to capture energy from their stars. Imagine a vast structure enveloping a star, designed to harness its energy output for technological use. While no actual Dyson spheres have been discovered, the concept isn't just science fiction. It opens up intriguing possibilities about the potential for extraterrestrial life and mega-engineering projects across the galaxy. For such structures to exist, a highly advanced civilization would need a level of technology far beyond our current capabilities, capable of lifting massive amounts of material into space for construction. The resources required to build a Dyson sphere would be staggering, likely involving the disassembly of planets or the use of asteroids. Validating the existence of these spheres is challenging. The light from a star would be altered in specific ways if surrounded by a structure capturing its energy. Scientists actively search for unusual light patterns using advanced telescopes, looking for signs of something unnatural that might suggest a Dyson sphere at work, such as infrared emissions that indicate a large object gathering heat. However, the sheer scale of our galaxy complicates the search. With hundreds of billions of stars, the chances of finding such a structure directly are slim, but it is not entirely outside the realm of possibility. Moreover, the existence of similar structures, like Dyson swarms, dispersed satellites orbiting a star instead of a solid shell, could prove more feasible. Such arrangements would maintain the balance of energy capture without the immense structural integrity challenges of a solid sphere. While Dyson spheres, or their equivalent, remain theoretical constructs, their potential existence prompts us to consider the capabilities and reach of intelligent life, as well as the future of human engineering in the cosmos. Whether or not we discover evidence of such structures, the very contemplation enriches our understanding of what might be achievable in the vastness of our galaxy. The discovery of an alien megastructure would ignite both excitement and intrigue, as it suggests the presence of advanced extraterrestrial civilizations. One of the most telling signs could be the observation of unusual light patterns from distant stars. Imagine a star whose brightness fluctuates in a way that cannot be explained by natural phenomena, such as planets transiting in front of it. This kind of irregular dimming could indicate the presence of an enormous structure, potentially harnessing energy directly from the star. Another indicator might be the detection of excess infrared radiation. While stars emit a significant amount of visible light and heat, advanced civilizations might construct solar collectors or habitats that capture and utilize this energy. Should we observe a sizable amount of infrared emissions from a region in space that seems out of place, it could point to artificiality and suggest that these structures are converting stellar energy for their own use. Additionally, the structural integrity of such megastructures may create unusual gravitational effects. If physicists detected anomalies in the movement of celestial bodies nearby, it could imply that there's something large and massive exerting gravitational influence, essentially a cosmic footprint left by an alien engineering project. This could stimulate further investigation into the object hosting these behaviors. Lastly, should we ever discover signals or communications that are distinctly structured and purposeful, that would be a groundbreaking sign pointing to intelligent life behind such constructs. Whether these signals are electromagnetic in nature or involve modifications of light from distant stars, they would be compelling evidence of an advanced civilization at work. As we scan the cosmos, each observation must be meticulously analyzed. The universe is vast, and while the possibility of alien megastructures remains speculative, the hunt could unveil extraordinary truths about our place in the universe. Stars with unusual light patterns can indeed intrigue astronomers and spark the imagination regarding the possibility of artificial interference. One of the most famous examples is KIC 8764, which demonstrated strange dimming behavior that some speculated might be caused by a massive structure orbiting the star, possibly indicating extraterrestrial engineering. This hypothesis was fueled by periodic dips in brightness that did not conform to the expected patterns created by orbiting planets. However, upon closer investigation, most such phenomena are ultimately attributed to natural cosmic events. For example, the light variations can occur from a star's pulsations, the presence of orbiting debris, or even the movement of stellar companions that might cast shadows across the star's surface. Such natural occurrences can mimic the light patterns we might expect to see from an advanced civilization. Astronomers employ rigorous methods to analyze these light patterns, using techniques like spectroscopy to understand the composition and behavior of stars. They study variations in brightness across different wavelengths, searching for signatures that could hint at non-natural origins. So, while unusual light patterns can evoke fascinating theories about artificial sources, the consensus is that most can be explained by the dynamic processes of the universe itself. Nonetheless, the search for extraterrestrial intelligence continues to inspire curiosity and scientific inquiry, fueling advances in technology and our understanding of the cosmos. The concept of advanced civilizations harvesting energy from black holes intrigues both scientists and science fiction enthusiasts. One of the most discussed methods is through a process called Hawking radiation, named after the physicist Stephen Hawking. This phenomenon suggests that black holes can emit small amounts of thermal radiation due to quantum effects. In simpler terms, near the event horizon, pairs of particles and antiparticles can be created from the vacuum of space. If one particle falls into the black hole while the other escapes, this escaping particle can carry away energy, effectively allowing the black hole to lose mass over time. In theory, a sufficiently advanced civilization could harness this escaping energy. Imagine a structure built around a black hole specifically designed to capture this radiation as it emerges. This would require technology far beyond our current capabilities, as dealing with the extreme conditions surrounding a black hole poses significant challenges. Another exciting concept involves capturing energy from the accretion disk around black holes. As matter spirals into a black hole, it forms a rotating disk, heated to incredibly high temperatures. The immense gravitational and frictional forces in this environment release huge amounts of energy, potentially usable if harnessed properly. Civilizations with advanced technology could devise methods to convert this energy into usable forms, akin to how we generate power from thermal sources on Earth. However, these scenarios remain speculative and depend on countless variables, including the materials required, the energy needed for practical implementation, and the challenges posed by the black hole's gravitational field itself. While these ideas ignite our imagination, they remain firmly in the realm of theoretical discussion for now. To confirm the existence of an alien-built structure, scientists rely on a combination of observation, analysis, and critical thinking. The first step often involves scanning the sky using powerful telescopes and other sensing technologies for unusual signals or patterns that do not align with natural phenomena. These observations might take the form of unexpected light flares or structures that exhibit geometric shapes, suggestive of artificial construction rather than natural formations. Once an intriguing signal is detected, a more detailed analysis is performed. This includes studying the object's composition and behavior. If a structure shows a consistent energy output, like the emission of radio waves or lasers, that seems intentional, it would generate significant interest. The next vital step is verifying that the findings aren't the result of natural events like meteors or cosmic dust. Scientists gather additional data, potentially using multiple instruments to cross-check the observations. Furthermore, collaborations between international space agencies and observatories can provide a robust framework for validation. Scientists would analyze archival data, searching for similar signals or structures recorded over time, which would help establish a pattern or ongoing phenomenon. If ground-based detections prompt further exploration, missions might be planned to investigate the area in question. This could involve sending robotic probes equipped with cameras and other sensors to collect live data, photographs, and material samples. Such direct investigations enhance our understanding, allowing scientists to look for materials or artifacts that could indicate artificial design. Throughout this process, rigorous peer review and a commitment to scientific skepticism are crucial. Each step, from observation to analysis to exploration, must be scrutinized to differentiate actual alien structures from natural occurrences, ensuring that any confirmed findings are credible and reliable. The hunt for extraterrestrial intelligence marries curiosity with an emphasis on meticulous scientific methodology, making the potential discovery of an alien-built structure not only fascinating, but a significant milestone in our understanding of the universe. As we delve into the advancements of 2024, a fascinating array of technologies has emerged, enhancing our quest to decipher the mysteries of space. One of the most notable innovations is the next generation of space telescopes, which have been equipped with highly sensitive instruments to capture unprecedented details from distant celestial bodies. These telescopes employ advanced optics and imaging techniques that allow scientists to observe faint light from astronomical phenomena many light-years away, opening a window into the early universe and potentially revealing new exoplanets that could harbor life. In addition to telescopes, artificial intelligence has begun to play a pivotal role. Sophisticated algorithms can now sift through vast datasets generated by these telescopes, analyzing and identifying patterns that human researchers could easily overlook. This extraordinary fusion of human intuition and machine processing power accelerates our understanding of complex cosmic events such as supernova explosions or the formation of galaxies. Moreover, advancements in propulsion systems have made headway, particularly in the realm of robotic exploration. New technologies have been tested that promise to significantly cut travel times for interplanetary missions, bringing far-off destinations within closer reach. These innovations may lead to more frequent and detailed explorations of areas within our own solar system, such as the icy moons of Jupiter or the dusty plains of Mars. Additionally, the use of small satellite constellations has expanded, enabling continuous monitoring of space weather and potential hazards like asteroids or cosmic radiation. These networks of miniature satellites work collaboratively to provide real-time data, enhancing our ability to respond to and mitigate risks that may arise from space phenomena. In tandem with these developments, space agencies around the globe are also collaborating more closely, sharing data and resources to pool their collective knowledge. This spirit of international cooperation ensures a concerted effort in solving fundamental questions about the origins of the universe and the potential for life beyond Earth. All these technologies and efforts point to an exciting future in our understanding of the cosmos, as we piece together the vast puzzle that is space exploration. The James Webb Space Telescope, often referred to as JWST, has revolutionized our understanding of the universe since its launch. One of its most profound contributions lies in its ability to observe distant galaxies, some of which formed when the universe was very young. With its advanced infrared technology, JWST can see through cosmic dust clouds and reveal hidden structures, allowing astronomers to witness the formation of stars and galaxies in unprecedented detail. Unexpected discoveries have come from JWST's observations that challenge existing theories. For example, scientists discovered galaxies that appear to have formed much earlier than previously thought, raising questions about how stars and galaxies could develop in such a short time frame after the Big Bang. This suggests that our models of cosmic evolution might need significant adjustments to account for these early formations. Additionally, JWST has detected light from exoplanets, revealing previously unseen atmospheric components, such as water vapor and other gases. This indicates not just the potential for habitability, but also the diversity of conditions that exist on other worlds. Such findings push the boundaries of our knowledge, showing that planets which might resemble Earth could exist in various forms far beyond our own solar system. Moreover, the telescope's capability to provide detailed spectra has allowed scientists to analyze the chemical compositions of celestial objects more precisely. This means not only confirming the presence of familiar elements, but also discovering unexpected chemical processes at work in far-flung regions of space. The James Webb Space Telescope has opened new frontiers in astronomy, enabling the unraveling of long-standing mysteries while presenting a host of unexpected revelations that challenge our prior understanding of the cosmos. Each observation adds a new layer to the complex tapestry of the universe, reminding us of how much there is still to learn. Yes, we are at a fascinating point in our understanding of the universe, where new technologies are allowing us to observe regions of space that were previously hidden from us. One of the most significant breakthroughs has been the development of advanced telescopes and observational techniques that can detect light from incredibly distant and faint objects. For instance, throughout the history of astronomy, much of the universe remained shrouded in darkness, either due to the immense distances involved or because certain wavelengths of light could not be captured by earlier equipment. However, modern telescopes, equipped to observe across a broad spectrum, including infrared and radio wavelengths, are now able to penetrate these obscured regions. This enhanced ability means we can gaze back in time through the universe's dust-laden veils, seeing stars, galaxies, and even entire clusters that formed when the universe was still in its infancy. The James Webb Space Telescope, for example, is allowing us to look at the formation of stars and galaxies just a few 100 million years after the Big Bang, a time when the universe was only a small fraction of its current age. Furthermore, recent advancements in gravitational wave detection have opened another window into the cosmos. By observing ripples in space-time caused by events such as colliding black holes, we gain insights into phenomena that were previously undetectable, shedding light on the universe's most violent and energetic processes. We are indeed encountering regions of space that we can now study for the first time, leading to a deeper and richer understanding of our universe's history, structure, and the fundamental laws governing it. Each new observation brings us closer to answering some of the most profound questions about the nature of the cosmos. New telescopes have the potential to revolutionize our understanding of hidden objects in our solar system. As technology advances, these instruments become increasingly sensitive, allowing astronomers to detect faint light and small movements that were once imperceptible. Imagine standing on a beach and gazing into the vast ocean. With a standard pair of binoculars, you might only see the waves crashing on the shore. However, with high-tech spyglasses, you could spot a distant lighthouse or even a ship far beyond the horizon. Similarly, advanced telescopes equipped with cutting-edge optics and enhanced imaging capabilities can capture light from objects lurking in the far reaches of our solar neighborhood. These telescopes utilize different wavelengths, including infrared, which can penetrate clouds of gas and dust that often obscure celestial bodies. This means that what may seem empty space may actually be bustling with the presence of unknown asteroids, comets, or even dwarf planets. Additionally, new survey telescopes are designed to systematically scan large areas of the sky over extended periods. This approach increases the chances of spotting objects that shift position across the backdrop of stars. As we expand our observational reach, we may not only discover new celestial neighbors, but also gain insight into their composition and behavior. Understanding the variety of objects in our solar system can provide clues to the formation and evolution of planetary systems, enriching our knowledge of the cosmos we inhabit. As we look ahead to the future of space exploration after the discoveries anticipated in 2024, the landscape is filled with potential and excitement. The next phase will likely emphasize deeper exploration of our solar system, focusing particularly on Mars and the icy bodies of the outer planets. Mars missions are expected to become more ambitious, with aspirations for sample return, which would mean bringing Martian soil and rock back to Earth for analysis. Understanding the composition of Mars could provide insights into the planet's past, including its potential to have supported life. Simultaneously, missions to the outer solar system will gain momentum. The icy moons like Europa and Enceladus may receive particular attention due to their subsurface oceans, which could harbor the building blocks of life. Upcoming missions might aim to drill beneath their surfaces to explore this hidden wealth of potential biological activity. Another exciting frontier involves the exploration of asteroids, especially those identified as potentially rich in resources. These bodies not only hold clues to the early solar system's history, but could also serve as stepping stones for future human missions or even harvesting materials for use in space. Moreover, advancements in technology are expected to play a crucial role. The development of more powerful propulsion systems could reduce travel time, opening doors to longer and more detailed missions. Innovations in robotics and artificial intelligence may also enhance our exploration capabilities, enabling more complex operations to be carried out remotely, especially in environments too harsh for human presence. In addition to robotic missions, human exploration is increasingly on the horizon. The Artemis program aims to return humans to the Moon, establishing a sustainable outpost that could serve as a launch pad for further exploration, including sending astronauts to Mars. The collaborative efforts of international space agencies will likely grow, pooling resources and knowledge to tackle the enormous challenges of deep space exploration. The discoveries of 2024 will act as a launch point, steering humanity towards exhilarating chapters in space exploration, with an emphasis on Mars, the outer solar system, resource-rich asteroids, and preparations for sustainable human presence beyond our home planet. Each next step is not just a journey into space, it is a profound quest for understanding our place in the cosmos. Cosmic rays are high-energy particles originating from outer space that continuously bombard Earth. Most cosmic rays consist of protons, but they can also include heavier nuclei and even electrons. Typically, scientists have a well-established expectation of their energy levels based on various astrophysical processes. However, some cosmic rays astoundingly exceed these expectations by immense margins. One key reason for these exceptionally high energies lies in the environments from which they originate. For instance, powerful phenomena such as supernova explosions and active galactic nuclei, regions around supermassive black holes emitting vast amounts of energy, are believed to accelerate particles to extraordinary speeds. When particles interact with strong magnetic fields or shock waves produced in these settings, they gain energy much like a child on a swing gets higher with each push. Additionally, there is a possibility that some cosmic rays could stem from interactions involving neutron stars or gamma-ray bursts, events with so much energy they produce spectacular flashes of gamma radiation. The interactions in such extreme conditions can lead to particles being propelled to energies not typically achievable in more commonplace cosmic events. Compounding this mystery is the role of magnetic fields in our galaxy and beyond. Cosmic rays can get caught in the grip of these fields, allowing them to travel long distances and possibly gain further energy along the way. This interaction hints at a dynamic universe where particles not only traverse vast expanses, but also engage in mechanisms that amplify their energies beyond what we initially expect. Thus, the existence of ultra-high-energy cosmic rays remains one of the intriguing questions in astrophysics, hinting at more complex and powerful processes within our universe than we currently understand. As researchers continue to study these cosmic visitors, they unlock the potential for new insights into the fundamental physics governing our universe. The concept of objects jumping between universes or dimensions is intriguing and often explored in science fiction. However, it touches upon serious theoretical physics. In some modern theories, particularly those involving string theory, our universe may not be the only one. It suggests a multiverse scenario where many different universes exist, each with its own unique laws of physics. In such frameworks, the idea of shifting between these dimensions or universes becomes a possibility, but not in the way one might envision a simple leap as we would experience in our everyday lives. Instead, transitioning between dimensions would likely require extreme conditions or mechanisms, perhaps utilizing energy levels far beyond what we encounter in normal experiences. Think of it as needing a key to unlock a door to another room. Without the right conditions, that door would stay firmly shut. Furthermore, our understanding of dimensions varies. In physics, we often consider multiple dimensions beyond the three spatial ones we are familiar with. These extra dimensions could be curled up on themselves, compact in ways that keep them hidden from direct observation. Objects moving through space-time might interact with characteristics of these hidden dimensions in ways that could, theoretically, allow for unique phenomena. Yet, these ideas remain speculative. The mathematics and physics behind dimensional travel or jumps are still areas of ongoing research, and so far there is no experimental evidence supporting the actual movement of tangible objects between universes. It remains a captivating subject of discussion rooted in profound theoretical exploration rather than proven science. Throughout this year, several remarkable events have occurred in space that challenge our understanding and inspire deep curiosity. One of the most striking incidents highlighted the enigmatic behavior of fast radio bursts, intense bursts of radio waves originating from distant galaxies. This year, astronomers observed a unique pattern from a particular source, suggesting that these mysterious signals may exhibit a level of complexity previously unseen. While some bursts are fleeting and only detectable for mere milliseconds, this source emitted a repeating sequence, raising fascinating questions about its origin and the astrophysical processes at play. Another captivating event was the unexpected dimming of a massive star located in a distant galaxy. This phenomenon puzzled astronomers, as the usual explanations, such as dust clouds or the star transitioning into a different stage of its life, did not fully account for the sudden dims. The star seemed to vanish for a period before re-emerging, which leads researchers to hypothesize about possible interactions with nearby celestial objects or even new types of stellar behavior that are not yet well understood. Additionally, scientists are still grappling with the nature of dark matter and dark energy, which seem to account for a significant part of the universe's mass-energy content, yet remain elusive. This year, there were observations suggesting behaviors in the cosmic microwave background, the afterglow of the Big Bang, that challenge existing theories of these dark components. These observations not only stir debates in the field of cosmology, but also hint at a greater mystery that continues to unfold. Each of these events sparks essential discussions within the scientific community, highlighting our ongoing quest to unravel the wonders of the universe. As researchers gather data and formulate new theories, they inch closer to answering some of the most profound questions about the cosmos, reminding us that in space, the unexplainable is often just the beginning of a new adventure in discovery. When faced with phenomena that seem to evade explanation, scientists embark on a journey of exploration and inquiry. Their first step is often observation. By studying the details of the event or object in question, they gather data that may reveal patterns or insights. This could involve everything from meticulously measuring celestial movements to recording unusual occurrences in the laboratory. Once they have collected sufficient information, scientists formulate hypotheses. These are educated guesses that attempt to explain what has been observed. The process emphasizes creativity and imagination, as sometimes the explanations proposed can be completely novel and untested. Importantly, these hypotheses must be measurable, allowing scientists to design experiments or observations that can substantiate or disprove them. After putting their hypotheses to the test, scientists analyze the results. If the findings align with predictions, the explanation gains credibility. If not, the scientific community may reevaluate the hypotheses or explore new ones. This iterative process is fundamental to scientific progress. Collaborative discourse is also a key aspect. Scientists share their findings with peers, leading to robust discussions. This communal approach often allows for different perspectives and further experimentation, which can illuminate aspects of the phenomena that an individual might overlook. Moreover, when encountering particularly perplexing phenomena, scientists may expand their exploration beyond traditional frameworks. They can look into interdisciplinary approaches, drawing insights from physics, biology, and even technology. Over time, even the most baffling mysteries can yield to the rigors of scientific inquiry. While some phenomena may remain enigmatic for a substantial period, the collective efforts of the scientific community ultimately work towards deepening our understanding of the universe's workings. In the vast expanse of the universe, there are indeed mysteries that may evade our understanding indefinitely. The pursuit of knowledge is a hallmark of human curiosity, but the complexities of nature often outstrip our capacity to fully decode them. Consider, for instance, the sheer magnitude of the cosmos. With billions of galaxies, each containing billions of stars, it's conceivable that some phenomena exist beyond our reach. One captivating example is dark matter, which makes up a significant portion of the universe's mass, yet eludes direct observation. It plays a role in the gravitational dance of galaxies, influencing their movements without emitting detectable light or energy. Despite advanced technologies and methodologies designed to unveil its secrets, the question of what dark matter fundamentally is remains largely unresolved. This could be a mystery we never fully grasp. Another intriguing case relates to the very foundations of physics, such as why the fundamental forces of the universe behave as they do. While we have theories that explain interactions at very basic levels, a cohesive theory of everything eludes even the most talented physicists. Such a comprehensive framework would seamlessly integrate all known forces, but it may involve principles or dimensions of existence that are currently beyond our comprehension. Then, there are the enigma-laden boundaries of consciousness and the origins of life itself. Despite technological advancements and breakthroughs in chemistry and biology, understanding precisely how conscious experience arises from mere biological processes is an ongoing challenge. The complexity of life's beginnings, tied to conditions that may no longer exist on Earth, deepens this mystery further. Ultimately, while our quest for knowledge may illuminate countless shadows in the dark, certain enigmas could remain sealed within the fabric of the universe, preserved as timeless questions that stimulate our imagination and ignite our search for answers. Understandably, some mysteries may be eternally woven into the cosmos, rewarding us with the thrill of inquiry while reminding us of the limits of our current understanding.